many contributions on open heavy-flavour as well as Quarkonia and on the X as well. And also we have a contribution on nuclei, light nuclei. So it's a very dense, and we look forward to a lively session. And yeah, so I remember the speakers that their talk should last for 20 minutes plus 4 minutes questions. So I will notify you when you are at 15 minutes. So when you have only 5 minutes left. And yeah, instead, I remember all of the participants that there is a message. Okay, so I remember all the participants that to ask questions, they have to use the raise hand button, or they can also use the Mattermost channel dedicated to this session. Okay. So after this message from the organizer finishes, I think we can start. Currently, there are 15 participants. And yeah, I don't know how many on YouTube, but there is also the YouTube channel that is followed by people. Okay, Jerome, thank you. You can start sharing, okay. And you can start.
Okay, thank you very much for the introduction. So I want to present you today the Dilepton measurements with Alice at the LHC. And just as I'm the first speaker here, I want to shortly motivate why we want to measure dileptons in the first place. So we have a rich topic of physics we can probe with the dileptons, depending on the different collision systems. So starting with lead-lead, where we can basically probe the chiral symmetry restoration with a modification of the vector mesons, the emission of thermal radiation, decorrelation of heavy-flavour pairs in the medium, or in peripheral collisions, we can even measure coherent photoproduction. In P-lead collisions, we then can study the cold nuclear matter effects like shadowing or energy loss, or even if we look into high multiplicity, we can look for an onset of thermal radiation here also. Then we have finally the PP collisions, which mainly we use as a vacuum baseline for the P-lead and lead-lead studies in order to pin down the heavy-flavour production and other processes like Jiayin or direct photon production. On top of that, we also can use PP to, of course, search for new phenomena in high multiplicity events as well, or if we look into very low momenta where QCD is not really fully understood yet. So just as a short outline of what results I want to present you today, what I really want to highlight here is that all results which I show you here in PP and P-lead are recent results which we released this summer. And two of them, the PP and P-lead at 5 TeV and the 13 TeV soft Dielectron production, are even published this summer. And you can find the archive link here highlighted in blue and later on in the talks on the top right corner on the respective slides. So let me jump in on how we measure the dileptons, starting with low mass dielectrons. We measure at mid rapidity, which I show here by these gray arrows. So we measure this in the central barrel, and we use at first the inner tracking system for vertexing, tracking, and PID. Then following this with a time projection chamber for mainly using the PID capability and the tracking to identify the electrons. And finally, at higher PT, we can use the time of flight detector. For rapidity, we use the V0 to do a multiplicity estimation of the event as well as the triggering for the events itself. For the dimuons, the situation is a bit different since we measure them in forward rapidity. And we use here the ITS, the inner tracking system for vertexing and the multiplicity estimation at mid rapidity. And with 0 basically for the event triggering and use on top of the muon trigger and the muon tracking. Finally, on the bottom left, you see here the different system and the luminosity of the data we analyzed, which I present you here today. So let me jump straight to the results, starting with a Dielectron production at 5 TeV in pp, which is the first measurement of this Dielectron production at 5 TeV. And what you can basically see here in this plot, you can see the data in blue compared to a hadronic cocktail shown here, the sum in black, with the two components of a light flavor here shown in green. The different heavy flavors in CC bar and BB bar in red and magenta, and finally the shape psi at high masses. What you can see if you look into the ratios, that the data agrees well with a hadronic cocktail. So what this means is that it's fully explained by hadronic decays, basically. And this is an important baseline for the following PLED and LED measurements at the same center of mass energy. So what this further allows us is to extract heavy flavor production, to extract the heavy flavor production cross sections in the intermediate mass region, so between 1.1 GeV and 2.7 GeV, and we do this by two-dimensional template fits in the invariant mass and per PT. And you can see both spectra here on the left, the invariant mass, and on the right, the per PT. And the different templates which we extracted from POEC and the solid lines and from PYTHIA and the dotted lines. And you can see basically by the individual fits which we done here that we have some model dependence, and the extracted cross section you find here in the table below. What is interesting here is that that we are really sensitive basically to the implementation of a heavy flavor production in these models, essentially in the initial correlation of CC bar or BB bar quarks. And this extracted cross-section we can also compare to previous measurements which we have done in 7 and 13 TeV, which you can basically see here on the left for CC bar and on the right for BB bar. And basically what you can see it that they basically are consistent with also an independent measurement of a heavy flavor cross-section at mid rapidity at 7 TeV, which you see here by this open square. And overall, funnel describes the data and the center of mass dependence well within the model uncertainties. So following this, we can go to PLED at 5 TeV, which is also the first measurement of this kind. And what we have done here for the heavy flavor production is that we use the cross section which we extracted in the PP collisions at the same center of mass energy and apply an N-call scaling, which overall reduces our systematic uncertainties of a cocktail compared to previous iterations. And you basically see the result here again on the left plot, where you can see again comparing the data in blue to the hadronic cocktail sum in black, that we see little deviations from the vacuum expectation. So we see no significant, we see no strong cold nuclear matter effects in the intermediate mass region. So we assume that they are rather small in the system. However, to further or have a better comparison, we try to have a data-to-data comparison to eliminate basically the uncertainties of the cocktail, which I'll show you here on the next slide. So this is the PLED, where we basically plot the PLED data over the scaled PP data, which basically is an N-call scaling. And if you look into the low mass region, so below 1.1 GeV, so this region over here, we see that we have a different scaling for the light flavor production. You can see the amount of light flavor shown here by this green area. So at least half of the produced particles are here from light flavor, and you basically see here again the peaks of resonances. And you can see that also this ratio follows the same trend. And if we go then to the intermediate mass region at 1.1 GeV and above, you basically see that the data is consistent with unity. And we see also here the comparison of the solid black line, which is again the cocktail from the previous slides. You can basically see that this mainly follows the same orientation and is also consistent with unity at intermediate mass region. Further on, we have comparison to theory expectations. So we included in our hadronic cocktail, so the black line, also additional effects of, for example, shadowing, which we use EPS 9 here. However, it seems to be disfavored, especially in the intermediate mass region. So for d mesons with a high PT of 2 GeV. However, in the lower invariant mass region, it seems to help us to describe the data on top of hadronic decays. Furthermore, we have thermal radiation, a calculation here by Ralph Rapp, which seems to overestimate the data in the low mass region. However, seems to improve our agreement in the intermediate mass region at higher masses. So what it seems to be here the case is an interplay of these two effects. So it's really important in the future to disentangle these two different sources. And we looking here forward to do two different basically approaches. First, basically have a suppression of non-prompt decays. So for example, the d meson decays by a topological approach, or selecting really high multiplicity events where we expect to have basically this onset of thermal radiation, if there is any thermal radiation in PLED at all. So continuing with LED-LEDs, so next system, and I'll show you here the most central LED-LED events. Outer preliminary, and what you can see here again is that the data is consistent with hadronic cocktail in the pi0 and in the JAPE psi region, which is something like a standard kernel for us in this measurement, as these hadronic cocktail contributions are from independent measurements. So basically, we use this to see if that our overall scaling of hadronic cocktail is correct, which seems to be the case. And if we then look into the intermediate mass region, we seem to see here a hint for a suppression, so which hints at a modification of the heavy-flavour production. And here we, at the highest energy densities in LED-LED, we basically expect the strongest medium effects. And if we then go to lower invariant masses, so between above the pion mass up to 500 MeV, basically, there seems to be a hint for an enhancement also, which may hint at prompt and thermal photons from hadronic gas. And we can basically look a bit closer into this region. So you basically see here on the left zoom in. So invariant mass, we only go up to 1.7 GeV here. So really to highlight this low mass region. And we compare it here, basically in the dotted line, you see the hadronic cocktail from the previous slide. And you see in the solid lines here, the calculations by Ralph Rapp, which seems to overall increase our agreement with the expectation of a hadronic cocktail. So it's consistent with QGP radiation here. And we can also do the same exercise we did before and basically plot here the RAA, so a comparison again to the scaled PP. And what you can see here is basically that we are still missing some significance to really pin down this excess at low invariant masses. However, we still have a high statistic data set from 2018, where the current analysis is still ongoing, where we expect to have 10 times more statistics in the central collision sample and 9 times more statistics in semi-central. So continuing with LED-LED, there's another region which we can look into if we look into very peripheral collisions. Here we see a clear axis observed on very low PT, basically, which is consistent with Korean photoproduction, where you can see a small comic of a production mechanism on top here. So this is really the electromagnetic fields of the two nuclei basically interacting in very peripheral collisions. We can see this contribution here at very low PT by this peak here. And this seems to be similar to observation made or published by Star, which you can find the link here. And also here we plan to have more differential studies with 2018 data and look into the event plane angle dependence as well as to the sensitivity of magnetic fields created. Overall, the production at very low PT is not fully understood yet. And what I want to stress here is an old result from the AFS experiment at the ISR, which measured an excess of dielectrons over expectation of a non-hadronic sources in an elementary collision system in PP. And similar effects were also observed in the real photon channel as well. And this doesn't seem to be the same effect which I showed you before, since in PP the magnetic fields are much smaller. And the excess here found is basically at very low event masses, so above 50 MeV up to 600 MeV, and at very low per PT below 1 GeV. And ever since this result here by AFS, shown on the right, no other experiment could really probe this region. However, with ALICE, we had dedicated low B field campaign where we reduced our magnetic field from 0.5 Tesla to 0.2 Tesla, which then allowed us to have an electron selection down to 75 MeV, on top of a better TOF acceptance and conversion rejection, which for the first time allows us to really challenge these IFS results. And we can see the results basically here. On the left, the invariant mass spectrum again, on the right, the per PT spectrum. And we can see basically that we also observe a similar enhancement at LHC energies. So above 50 MeV, basically, we see a deviation from the expectation from hadronic decays only, which seems to extend above 600 MeV, basically. And if we look into the per PT spectrum, we see that this enhancement is basically completely located at very low PT, mostly at the very low PT bin here. And basically the enhancement factor which we extracted, you can find here, written down here. As you can see, our most limiting factor is here the hadronic cocktail. And the dominating contribution here in this region, as you can see here by the blue line, is the eta meson. And unfortunately, with ALICE, so far we only have a measurement down to 400 MeV, which you basically see here in this bottom plot by these red points here, which stop at 400 MeV. And as you can see, a comparison to MT scaling, which completely overshoots the eta production at low PT. So we cannot use MT scaling. And so what we did instead is that we use the Saris and Tup measurement to constrain basically our expectation at very low PT. And you can basically see here the solid black line is our expectation we put in here in our hadronic cocktail. So we did further studies of this enhancement by looking into the multiplicity dependence, which you can see here on the left. And you can basically see the enhancement region here plotted in orange, basically. And I'll show you a small sketch of the phase space basically probed here in the invariant mass and per PT. In orange, you can see basically here the enhancement region. You can see on the left, basically, that we see the enhancement above the hadronic cocktail as a function of multiplicity, which seems to be most consistent with a linear scaling, basically. And if you look into the two control regions, so at lower invariant masses, but the same PT, we see no enhancement, as well as if you look at higher PT, but the same mass, which is shown here in green, we also see no enhancement. Furthermore, we extracted the acceptance-corrected excess yield and compared this to theory predictions. Here again, in red, a calculation by Ralf Rapp, and in green, a calculation based on hadronic Bremsstrahlung. You can see that data in both cases exceeds the description of these calculations, basically. And what is really needed at this time to increase the significance of this excess is an independent measurement of the eta measurement, also in the same low field data set. Okay, continuing and coming finally to the dimuon production, I'll show you here the multiplicity dependence. measured for the omega and the phi in pp at 13 TeV also. And you can basically see the different multiplicity classes shown here and by the different colors compared to the minimum bias shown here in black. And in the ratio you can basically see the different behavior. And here one point is that the multiplicity is estimated independently at mid-rapidity to avoid any correlation here. What is interesting here is if we look into the self-normalized yield compared to Pythia, and we show here basically the different Pythia modes with different colored with the colored lines with the different line shapes. And if we look into high PT, so above 6 GeV up to 8 GeV, we see that the high PT production of omega and phi is well described by Pythia, and we are not really that sensitive to the different mechanisms. However, if we go to low PT, we can see that we are much more sensitive now to the different production mechanisms, especially if you look into the phi. And we can see basically that we only need hadron scattering in order to describe the phi production here. However, if we look into the omega production, there seems to be that we need an additional suppression mechanism in order to explain this production here. So overall, we need further insight on the hadronic production here in high multiplicity events at low PT. Which brings me to the outlook. So for the Dilepton production at run 3 and 4, we will have a new ITS and upgrade our TPC to a gem-based readout system, which will improve our vertex pointing resolution by a factor of 3 to 6, which will further improve our topological separation, which I showed or motivated before, as well increase our readout rates in LED by a factor of 100. On top of this, we will have dedicated Dielectron runs with reduced magnetic fields again, and we plan to overall increase our statistics in PP by a factor of 400, which will then allow us a more precise multi-differential analysis. And based on this, we have a new public release where we basically illustrate our PP plans for run 3 and 4, which you can basically find the link here on the top right. On top of that, we will have our first LED runs with a low field setup, where we plan to study the soft dielectron production in the media. On top of that, we also have the installation of a muon forward tracker, which allows us the tracking before the absorber with a new silicium tracker, which will overall improve our pointing accuracy in the dimuon analysis. Which will bring me to my summary. I showed you dielectron measurements in PP, PLED, and LED at 5 TeV. In PP, we established the baseline for PLED and LED with a PT cut of 200 MeV, as well as extracted the heavy-flavour production cross-sections. In PLED, we have found no significant modification of the heavy-flavour production yet. However, we see a hint for suppression at smaller masses, and we with a comparison to models at this point, we expect a larger suppression with what we see. And if we look into LED, we see also possible access at thermal radiation at low invariant masses, a suppression of a heavy-flavour at higher masses, and a low PT access as well in peripheral collisions. And furthermore, I showed you the soft dielectron production at 13 TeV, where we saw an enhancement of a hadronic cocktail expectation, so from hadronic decays, an additional source here, which is not explained by these, and also showed here the multiplicity dependence, which is so far inconclusive. Finally, I showed you the omega and phi production at forward rapidity at 13 TeV as a function of multiplicity, where we seem to be sensitive to the production mechanism at low PT. Thank you.
Thank you, Jerome. So now it's time for a question. So participants, please raise your hand. So there is no hands raised. Let me check the Mattermost channel. Nothing. So I have a question concerning this access in PP collisions. You show very interesting results, and also that models to which you compare the data do not seem to catch the trend. So
Yep.
do you have, I mean, some interpretation of these axes, and also what are the further experimental measurements you need and you expect to be able to do in the future to better understand it?
Okay. So one thing, so regarding the source of this is really not clear. Where in the past, for the old results, basically in the photon channel, there were different mechanisms proposed here, going from color chromodynamic radiation, basically, and the soft dielectron, soft quark annihilation in a cold QGP or something in this direction. It could basically be something with a incoherent photo production, basically, of a magnetic fields, or something like, yeah, there are all kinds of different mechanisms, but at this point we are still too far to pin down any of this. So this is why the multiplicity dependence here would be also important to pin this down. So what we plan to do here in the future is to really look into this first spin here. As you can see, the hadronic cocktail expectation here really goes down. So our overall hadronic background disappears here, and we are basically most sensitive in this very low PT region. And we try to have a better resolution here and to extract basically a more significant result here.
Okay, thank you. So I don't see hands raised. So thanks again, Jerome, and we can move on. So
thank you.
Wolfgang?
Yes, very well. Can you hear me, see me?
Yes.
Try to share the screen, share. 5. Okay.
You can start.
Thank you. Okay, so I would like to present some results of our theoretical description of the interplay between thermal and gamma-gamma induced production of dileptons, in this case dielectrons. And I will give you first a brief reminder of the peripheral, alter-peripheral collisions and the Weizsäcker-Williams fluxes of equivalent photons, and then I come to our description of semicentral or peripheral collisions and compare to the RIG data. And in the end, I will show some recent development of a density matrix generalization of the Weizsäcker-Williams approach, which we are applying now to confront also the higher energy data at ALICE, for example. So you are all familiar with the Weizsäcker-Williams photons, that nuclei which have large charges are accompanied by a coherent photon cloud. And this photon cloud can be essentially used like partons, which induce various photon-induced processes on the nucleus, for example. And if you're looking at large impact parameters, you can calculate these fluxes easily just from the classical field theory textbooks. And anyways, the formalism is naturally formulated in the B space. Now, in our case, we are not interested in the alter-peripheral collisions. We will often have smaller or intermediate impact parameters, so it's important to take into account the finite size of the nucleus. And this is done by recalculating these E fields with incorporating the electromagnetic form factor of the nucleus. And here you see such a realistic electromagnetic form factor, which is basically a Fourier transform of its charge distribution, which we use in our calculations. Okay, so alter-peripheral collisions have been discussed quite a bit already in other talks yesterday. And it's really the main place where these coherent Weizsäcker-Williams photons come into play. So these are collisions in which nuclei do not have strong interactions between each other. So they pass a large impact parameter between them. And you can produce, for example, Dilepton pairs, vector mesons, which also populate the Dilepton channel. And the crucial feature which links all these processes is that the produced system will have in generally very small PT. Okay, that is just because, you may say, because of the nuclear form factors which restrict the transverse momenta of photons to be very small. So if you think of these Weizsäcker-Williams photons as partons in the nucleus, it's natural to think why they shouldn't also play a role in inelastic collisions, right? This is essentially like, you could think that an event in which nuclei collide, that provides a sort of underlying event, and on top of this event, the coherent photons from the two nuclei can collide and can produce, for example, a dilepton pair. And that dilepton pair, in general, we will expect to have very small transverse momentum. So there have been some early considerations of such effects of the coherent photons in the pre-collider days, for example, by Gerhard Bauer and collaborators. But let's say the first serious hint of the relevance of photoproduction mechanisms in peripheral collisions that goes back to the Alice collaboration, who discovered a strong enhancement of J psi with PT of smaller than 300 MeV in peripheral collisions. And that was suggested by Mariola Krusek-Gawenda and Antoni Szczurek to be a sign exactly of this coherent photoproduction. So our question was just what is the interplay of this production mechanism with the more, well, dileptons, which we know from the classic thermal radiation, which are often used as a probe of the QGP. What is the competition with the mechanism, and so on. So we use the B-space formulation of the photoproduction, in which we calculate the cross-section of a E plus E minus pair produced at distance B1 and B2 from the nuclei, and as a function of the impact parameter between the nuclei. In interperipheral collisions, you will constrain this distance to be larger than the distance of the nucleus, than the size of the nucleus, so that there is no overlap. But in principle, we can calculate this B distribution anywhere, even in the region where nuclei overlap and where then the underlying event happens, an elastic event in which, for example, plasma can be produced. So this cross-section can be calculated in B-space in such a parton model way using the Weizsäcker-Williams fluxes. And we will calculate yields in a certain centrality class by integrating this B over the corresponding minimal and maximal B, which correspond to this centrality class C, and divide by the hadronic cross-section in this centrality bin. Okay, that gives us the yield of dileptons in such an inelastic collision. So the centrality in our case is directly related to impact parameter. We are doing the calculation impact parameter. So we are using a simple optical limit of Glauber model to determine this B min and B max. And this is very similar values as you get for the standard Glauber Monte Carlos. So this is just what is behind our calculation. And I can show you a B dependence of such dilepton production cross-section just for the pedagogical purpose. So this is calculated for a gold-gold collision from very low energy, from 50 GeV, 200 to 5 TeV. And the peripheral collisions, these are below, let's say, 15 Fermi, okay? These are the ones which we are interested in. And you see that above 200 GeV, this range of the impact parameter space is basically energy independent. What depends strongly on energy is the alter-peripheral tail, which rises with energy. Okay, this is often missed if people have often the intuition that these effects must rise with the energy, but actually in this B region, the cross-section is more or less constant. So the thermal part has been provided to us by Ralf Rapp. And this uses an approach which has been tested against a large amount of data, in which the dileptons are emitted from a fireball which evolves through a whole, well, through several phases, through the plasma phase, through the hadronic phase, and the non-trivial information is contained in this spectral function, which really contains all these dynamics. In the plasma phase, it will contain, for example, a QQ bar annihilation. And then in the hadronic phase, the in medium vector spectral functions, and everything is done in such a way that these descriptions match smoothly. And so there's a huge apparatus behind this. In this case, the formulation is evidently not an impact parameter space, and the centrality classes for the different colliding systems are just related to hadron multiplicities, and in the end it comes out that it is related to the initial conditions for the fireball. But these prescriptions also have been checked, so this is a somewhat different approach than the B-space, but let's not worry too much. So here I show you a comparison to the star data. These are invariant mass spectra of dileptons in a range of per PT smaller than 150 MeV, so very small PT dileptons. And on the left plot, you see the decomposition into different mechanisms. You see 3 different centrality classes from top. These are peripheral events, 60 to 80%, then 40 to 60, and semi-central 10 to 40. And in order to confront the data, of course, we need to add a contribution from the case of final state hadrons, the so-called cocktail, which was supplied by the star collaboration. And you see that in the most peripheral centrality class, the coherent photons basically exhaust the cross-section up to the J psi peak. I will comment briefly. At well, the middle, they also give the dominant contribution. And finally, in the semi-central, all contributions, thermal and coherent photons, are basically of the same side. On the right-hand side plot, you simply see the sum of all mechanisms, and you see that these invariant mass spectra are quite well, very well described. Exception is the J psi, and this J psi is simply not included in our calculation. It's the same mechanism as I alluded to in the introduction, which has been suggested by Anthony and Mariola to be due to coherent photoproduction, and that was indeed borne out by calculation by Jia and et al., who described this peak nicely. So this is a very satisfying description of the invariant mass spectrum. What about the PT distribution? As I have said, the PT is very small, so we should see this, the QT, we should see characteristic coherent peak at small PT. And in this, our approach, we calculated the PT distribution just from the integrated cross-section. Okay, so we show the PT distribution not depending on centrality class, but we show the integrated PT distribution over impact parameter space in terms of transverse momentum dependent photon distributions, where PT is simply the sum of the QTs of photons, and we have the on-shell gamma-gamma to dilepton cross-section. And this looks like this. These are, again, star data. And now it's not binned in centralities. These are different ranges of invariant mass from top to bottom, from small, well, lower side of the row, upper side, and well, somewhat above phi, below J psi. In general, you see, first of all, you clearly observe the coherent peak. And our PT distribution is reasonable, I would say, although the peak is a substantially smaller PT than in the data. But in general, the picture is, I think, very clear that this is really due to the coherent photon mechanism. We try to look also at the lower energies, the SPS energies, where also data at low PT have been measured. But here, the case is weak for coherent photon production. This is a small contribution here. Basically, only near the threshold it can have an impact. So then we simply presented predictions of invariant mass spectra for higher energies for the 5 TeV, as can be probed, for example, by ALICE. And as you have seen in Jerome's talk, this is being measured by ALICE. So here we see, again, we evolve from central to peripheral to more peripheral. And what is shown here is the gamma-gamma contribution and the thermal dilepton contribution. And you see that thermal dileptons at small masses dominate in the semicentral, whereas in the peripheral, again, we have a real dominance of the coherent photoproduced dileptons. So we were not able at the moment to calculate the PT distributions at the ALICE energy. I will come to this in a minute. And here you see the excitation function of E plus E minus pair as a function of center of mass energy. And this relates back to the plot which I showed in the beginning, to the B-space distribution I showed in the beginning. Clearly, there's a steep rise of the coherent photons up to about Rig energy, where it becomes flat. Okay, this is flat because it's almost exactly flat because you take the very restricted phase space. If you would take the full phase space, of course, with rising energy, there will be some rise because phase space increases. But if you're looking just in the central rapidity bin, then this is basically flat. Thank you very much. Yes, 5 minutes, I see. So here you see the thermal radiation, and it has the typical logarithmic dependence on energy. Actually, the Rig energy is about the optimal when it comes to the relative size of the coherent photoproduction, right? So it has the relative biggest effect just in the Rig energy range. So now let me, in the last minutes, just show how we want to extend our approach to calculate transverse momentum distributions, which now really depend on impact parameter, so that we can calculate the transverse momentum distribution faithfully in the centrality bins. And if you want to describe photons which at the same time I had some impact parameter and carry transverse momentum, you will be led to some sort of Wigner distribution, if you wish, constructed from the electric field vectors. And what is more important in this case is that you will need to have a polarization density matrix in here, Cartesian polarizations of the photons. So the cross-section will be now something much more involved. It will be convolution of these sort of Wigner distributions with a gamma-gamma to E plus E minus matrix element and convoluted over photon polarizations. This is different from the standard case. There's no independent sum over photon polarizations, okay? And it also differs, our approach somewhat differs from ones known in the literature, which are sometimes used by other groups. So we can write this cross-section more explicitly in terms of electric fields. And then what you will see, you can understand this a bit better. What you will see is that this sum over polarization, it turns out that simply in the gamma-gamma center of mass, you must imagine your colliding photons. They can be in Jz equals 0 or plus minus 2 states, okay? And at fixed impact parameter, these colliding photons the nuclei at fixed impact parameter provide you simply a mixture of photons in 0 plus, 0 minus, 2 minus, and 2 plus states. So this is the information of the sort of photon polarization becomes correlated with impact parameter. There's no independent sum here. And we have some preliminary results of these of PT distributions calculated within such an approach. And here I show the PT distribution of the pair for 60 to 80% central gold-gold collisions, for 200 JeV and 5 TeV. Just for convenience, I don't change the nucleus. Okay, of course, for Alice, you would to use lead, but to have it on one plot, I do like this. And what you see is that, first of all, the peak is in the right ballpark, as we know from the RIC data. And you also see that the peak doesn't run away towards a smaller PT. That would be the case if we use the formula of the integrated cross-section, because the QT distribution of photons is only cut off by the longitudinal momentum carried by the photon. And that becomes smaller and smaller the larger the energy. So in the integrated cross-section, you expect that this peak goes away towards smaller and smaller PT. Whereas here, you see that it more or less stays put. So, okay, these calculations are in progress. You can imagine that that's a bit of a tricky thing to do the Fourier transform of this multidimensional integral, but I think we will soon be able to confront the data which Jerome presented just a minute ago. So for a summary, we have studied the interplay of thermal radiation and photon-photon fusion for the case of low PT Dilepton production. And we get a good description of the recent STAR data in the 3 centrality classes where they published the data for invariant masses, okay, up to about 4 GeV. And yes, this is the measured range. So in the 2 more peripheral samples, the coherent emission is indeed dominant. In the semi-peripheral sample, it's still comparable to other mechanisms. The coherent photons are entirely negligible at low energies and must be taken into account only close to the threshold. And finally, I showed you development, how to go to calculation of impact parameter dependent PT distributions for which we need a density matrix generalization of the Weizsäcker-Williams fluxes. Okay, thank you. That's what I have for now.
Thanks a lot, Wolfgang, for this nice talk. So now it's time for questions. So participant, please raise your hand. Or write questions also on the Mattermost channel. So I don't see questions, but I have one indeed. So, well, from the, I'm an experimentalist, but
yeah.
So do you think that correlation measurements like angular correlations, so delta phi correlations or delta eta correlations may help to better interpret the experimental data? So could be this a feature for coherent emission?
Yes, very, very good. This is also, it's observably related to the PT of the pair, right? Because if PT of the pair would be 0, you would have back-to-back kinematics of the Dilepton pair, and finite PT of the pair gives you an azimuthal decorrelation of the Dileptons. That's indeed also an interesting observable which one should study. It's okay. It's closely related to the PT distribution in the case of the coherent mechanism. But it's an additional information. That's right. That's right. It's also calculable within our approach, and it's also interesting to look into. it would be also, yeah. Even things like sort of V2 of the pair could be produced by such a photon-photon fusion due to the fact that you are correlating B with PT sum. Okay, you're correlating this B with the PT of the pair through this complicated form that impact parameters correlate with photon polarizations, and the polarizations correlate with the production mechanism. So yes, answer is yes. It would be interesting measurement.
Thank you. There's a question from Michael Weber. Please go ahead.
Yeah, hi. I hope you can hear me. Michael Weber from Ali's collaboration. I have a question regarding one effect that we realized when we were doing this measurement. I was wondering, how do you take into account smearing effects? I mean, detector resolution. Is this for star done, or what do you plan to do on this front? That we can give you smearing matrices and you put it in your calculation, or can this? I mean, what is your take on this?
Is it easier if we give you a, say, say a PT distribution of the pair? I mean, we compared in the star case simply to the published data, right? To the published data. So I assume that these are sort of corrected. Excuse me?
I mean, usually the detector resolution is not unfolded, let's say.
I see.
At least this is not done in Alice. In star, I cannot answer now, but I guess.
I see. Because you know they publish PT distributions of a pair. So yeah, how to proceed best in this case? Of course, I mean we can convolute this with some sort of distribution which you would give us, but I don't know if this is up to professional standards, right? If it isn't better to use some theory distributions and then run them through the detector analysis, right? I mean.
Okay, thanks. Probably it's good we discuss again.
Yes, you can also keep on discussing on the Mattermost channel. Now we have to go on. So thanks again, Wolfgang. And can you stop sharing? Yes.
Yeah, stop sharing.
Okay, so Robin Caron from Saclay.
Yes.
The next speaker. So
do you hear me? Yeah.
Yes.
Okay, I will share my slide. Okay. Do you see the full screen? Yeah. Okay.
You can start. Thank you.
Okay, thanks. So good morning, everyone. So I would like to thank the organizer to give me the opportunity to talk and to present result about Bottomonium measurement in nucleus-nucleus and proton-nucleus collisions with Alice. So here I just put you some link to the recent publication and also result that I will present in this presentation. So just to start, and some physics motivation. So why do we need to study Upsilon in heavy ion collision at LHC? So clearly it's a unique and key system to prove the deconfinement property of the in-medium QCD force. And about the heavy quarks, so we have the CC bar and BB bar pair that are created at the very early stage in the collision. So this is why they experience the full evolution of the medium. So it's a very good probe. And they are also very sensitive to the early time non-equilibrium dynamics, so before the formation of the quark-gluon plasma. And about this heavy quark pair, so they can be a Bound state of heavy quark pair, so we call this a Quarkonium state, and it can be suppressed, and the level of Quarkonium suppression depends on the heavy quark pair interaction, and about the temperature of the surrounding medium. just wait. Maybe I can share my video. It's maybe with a, oh, yeah. Okay. Sorry for this. And also about on the left hand side. So I just show you the typical length scale with the radius r of the primordial fundamental state of the CC1 pair and BVR pair for the gypsum and epsilon. So we have the relative size with comparison with the standard light hadron. And on the bottom panel, we can see the standard spectral function for the Hess wave and for the epsilon state. And we can see the different curve corresponding to different in medium temperature. And we can clearly see the sequential suppression. And for example, for the fundamental state 1s, it can be survive up to 500 MeV temperature. Okay, so next slide here. Here on the left-hand side, I show you the relative size of the Bottomonium state. For the excited states for 2s and 3s, you can see that they are lighter binding energy. So they correspond to also lower dissociation temperature. And also about the BP bar pair, so they experience the full evolution of the medium, so they sensible to the each phase of the collision. So with the QGP formation and next with the chemical freeze-out and kinetic freeze-out. So which are the relevant observable to measure this Bottomonium state? So we have the nuclear modification factor. And so in order to study the AA or PA collision with respect to the PP collision. And we have also the azimuthal anisotropy with the VN coefficient in order to evaluate the degree of equilibrium of the quarkonium state, and also some path line dependent suppression effect. So here on this slide, I just show you the detector, which detector to use to measure this observable for this epsilon state. So in this analysis, we will use a silicon tracker, so the silicon pixel detector used to reconstruct the charge tracklet, also the primary vertex, and also used to reconstruct the event plane. And we'll use also the Visio detector. So it's correspond to scintillator on each side of the interaction point. So it is used as a trigger, also centrality estimator, and also as an event plane for determination. And finally, we'll use the muon spectrometer, used as a dimuon trigger and tracking, and used to reconstruct the epsilon state. And also all the measurements are accessible down to PT equals 0. And just on the bottom left side, I just show you the integrate luminosity for P-LED and LED data that we will use in this presentation. Okay, so here on this slide, I just show you the different collision systems. For example, for the P-LED, I just show you the corresponding forward rapidity range for P-LED collision and for LED-P collision for the backward rapidity range. And for PP and LED collision, we'll use the forward muon spectrometer, it's at forward rapidity. Okay, so here, just show you how to define the epsilon production in P-LED and LED collision. So basically, the LED collision are used to study the hot matter effect. So due to the presence of the quark-gluon plasma. So for the quarkonium, so we'll study the suppression versus the regeneration effect. Regeneration, it's a recombination of the two heavy quark. And for the P-LED collision, so they used to study the core nuclear matter effect. So it's related to the modification of the parton distribution function in the nucleus, called as shadowing, or also the energy loss of the heavy quark pair. so that are produced and then traveling through the medium. And we have also some final state mechanism like come-over interaction, also absorption. So about the level of separation, so it's quantified by the factor, the nuclear modification factor. So here for the lead collision, for example, we will just do the ratio of the yield in lead collision over the yield in PP collision, and also scale by the nuclear overlap function. And we can do also similarly for the P-lead collision. So basically, in this presentation, we'll investigate this nuclear modification factor as a function of centrality of the collision and rapidity and PT. And we'll also compare to the theoretical model. And here on this plot, it corresponds to the invariant mass in the diamond decay channel for the 1s, 2s, and 3s state for the epsilon side. Yes, at forward rapidity. So here on this slide, I show you the epsilon cross section. So on the left hand side, it corresponds to the epsilon 1s. So in red data, it corresponds to forward rapidity, and in blue, it corresponds to the backward rapidity side. And on the right hand side, it corresponds to the cross section for the 1s, 2s, and 3s state at forward and at backward rapidity. So we can see a clear modification of the epsilon 1s, 2s, and 3s cross section in P-lead collision compared to the normalized PP collision. So it corresponds to the shaded band. And also this effect on the cross section are more pronounced at forward rapidity than at backward rapidity, if we can see on the left hand side. So here on the next slide, I show you the nuclear modification factor as a function of transverse momentum. So on the left hand side, it corresponds to the backward rapidity side, and on the right hand side, it corresponds to the forward rapidity range. And so we can see that at very low PT, there are some indication of a slightly stronger nuclear matter effect, and also about the model. So it corresponds to different shadowing calculation, and also in each side they suggest a flatter behavior that we cannot reproduce for the backward rapidity range. And also at intermediate PT, so all the data are compatible with unity and also the nuclear PDF fits. Okay, so here now I show you the nuclear modification factor as a function of rapidity. So it's for the epsilon 1s state on the left hand side, and it's a nuclear modification factor for the 1s, 2s, and 3s on the right hand side. So we can see that on the left hand side we have consistent result on epsilon 1s nuclear modification factor between Alice and LHCb, and also at backward rapidity we have some tension between data and also shadowing and energy loss model. And so here about the model, we have some model based on the shadowing effect, models about energy loss effect, and also we have a model corresponding to the come-over interaction. So also on the right hand side, we have a comparison to the come-over interaction, and we can see that the come-over based model predicted backward rapidity, an ordering of in the separation of epsilon 1s, 2s, and 3s, but we cannot see this with the data. Okay, so now I will move to the lead-lead collision, and I just will present the two theoretical models for epsilon nuclear modification factor. So first we have the transport model from TMU. So it is based on the kinetic rate equation, also an isotropic fireball. And they implement also the regeneration mechanism, but for the Bottomonium, it's very, very small due to the low number of BB pair created in the collision. And on the right-hand side, so there are another model based on the hydrodynamical model. So it's based on the hydrodynamic equation, and also by modeling the medium by viscous anisotropic medium. They don't implement regeneration mechanism. So they use also different dissociation temperature for epsilon 1s, 2s, and 3s state, and also different parameter. But also a crucial ingredient, it's the percentage of for the Findorn fraction and the direct production for the epsilon 1s, which correspond to approximately 67%. Okay, so now on this slide, I show you the nuclear modification factor as a function of the centrality, or here it's the number of participants in the collision, lead collision. So if we move to left to the right hand side, it corresponds to peripheral on the left and central on the right. And we can see a clear and also stronger suppression in most central collision, which is in agreement with both models. So hydrodynamical model on the right and the TMU on the left hand side. And you can also see that the RAA for the epsilon 2s it's smaller than the epsilon 1s by about a factor of 3. Okay, so now I will present you the nuclear modification factor as a function of transverse momentum on the left-hand side and as a function of rapidity on the right-hand side. So we can see that the comparison with model, we have agreement with the data. And we can also see that there are no significant dependence of the epsilon 1s area as a function of PT. And about the rapidity side, so we can also see that there are slight rapidity dependence, which is opposite to the hydrodynamical model prediction. Okay, so now I move to the other observable that is very interesting is the azimuthal anisotropy in lead-lead collision. So here in non-central collision, we can have an overlap region, and this overlap region, when the QGP is formed, have an ellipsoid shape. So this shape have a spatial anisotropy, and due to the high pressure gradient and also some interaction with the constituent, it can transfer to the momentum space anisotropy. So basically, it's the high pressure gradient will drive the anisotropic flow in the liquid, and so we can ask if the epsilon states are sensible to this collective effect. So basically, we have the elliptic flow coefficient, the V2. It's corresponds to 0 if the emission is isotropic, and if we have momentum space anisotropy, the V2 coefficient will be higher than 0. So it means that we have particles are reflecting the flow of the medium. So about the epsilon 1s, so we have said that dissociation will be only limited to the first stage of the collision due to the very high dissociation temperature. And also about the QGP, so we have a very fast cooling. So this dissociation will be only possible at a very early stage of the collision. And also we can there are also possible contribution due to on the elliptic flow of the epsilon 1s, maybe due to the Findorn, that there are non-negligible part. So from the 2s, 3s, or also the KIB state can participate because they are lower dissociation temperature. So they are longer. They live longer time there are longer time in the medium, so they can inherit their flow from the medium. Okay, so on this slide, I just show you the Upsilon 1s elliptic flow measurement. So it's an invariant mass on the left-hand side, and the V2 profile as a function of invariant mass on the right-hand side. So the method that we use is a standard scalar product method. So on each diamond pair, we use the azimuthal angle, and we apply the product on the even flow vector, the Q vector, which corresponds to the sum over all charged particles in one event. So we apply this scalar product, and we average over all all diamond, and this will produce this profile V2 as function of invariant mass, and we can extract the V2 of Upsilon 1s state here in red. Okay, and now just show you this V2 measurement as a function of PT, and so it's corresponding to the first measurement of Upsilon 1s in lead collision. So the measurement give a V2 of Upsilon 1s compatible with 0. It's very interesting result because it's the first time that we see a V2 equals 0, because all the measure hadron have V2 higher than 0, and also in contrast to the GIPSI have a lower mass, and the GIPSI measurement give a V2 higher than 0 also. So we can see that the V2 of Upsilon 1s is 2.6 sigma lower than the GIPSI. And about charmonium side, so there are talk from Alexandra today on charmonium measurement, which we have also new result and interesting result. And about the Upsilon 1s measurements V2, so there are also CMS, there are latest publications that confirm also this measurement of compatible with 0. And also this measurement, it's also, there are big statistical uncertainty, and it's compatible with the transport model also, and also from hydrodynamical model, which are based on anisotropic escape mechanism, the BBGS model. Okay, so this brings me to my summary. So about the P-lead collision, we can see that the Upsilon measurement helps us to study the nuclear effect in absence of the deconfined medium. So in order to disentangle the QGP effect to the CNM effect. And we can also see that we see a stronger nuclear matter effect at very low PT. And also all the models which are based on different CNM effect can describe the data at forward rapidity, but overestimate at backward rapidity. And about the AA and also the V2 measurement of Upsilon. So this helps us to determine also or evaluate the temperature of the early stage of the QGP. And we can see that we have a stronger suppression in central collision. And also the Upsilon 2s are very suppressed, 3 times more than Upsilon 1s, which is also in agreement with the model. And about the V2 of Upsilon 1s, so it's compatible with 0. And this indicates that clearly the dissociation will be only limited to the first stage of the collision. And about this measurement of Z2 for the BOT, so there are also new insights on BOT fuel, and there are talk this afternoon about BOT production from Xinye Peng. So yeah, I finished. Thank you for your attention.
Thank you, Robin, for the very nice talk. So now it's time for question. So participant, please raise your hand or write it on Mattermost. So I have actually a question. So concerning the Upsilon V2,
yes.
what do you expect to be able in terms of precision in the future, even in round 3? Can you, how much can you reduce the uncertainties? Can you try to go higher in PT? Do you know what is the maximum V2 expected, even above the measured range from theoretical expectations?
Yes, there are some perspective for the Alexandra 3 and 4. So we done some simulation for predict what will be the higher precision for the upgrade. So for the Upsilon 1s, there are very big improvement, I think, for the V2 of Upsilon 1s. And so I don't know if we will be able to discriminate with some model, because each model based on very different mechanism are very similar prediction. So maybe we need to wait to very, very high statistics. But it will be also possible to maybe to extract the Upsilon 2s state V2, which is very interesting measurement, because model predict very higher V2 for Upsilon 2s. So it will be very interesting measurement, and yeah.
Okay. Yeah. Also the what you observed, the rapidity dependence in PLED was very interesting. Okay, but I see a question from Yuri, so I let him go. Yuri, please go ahead. Yeah.
Yeah, thanks. That's maybe rather a comment. So you mentioned that one of two models is this TAMU, which relies on the assumption of isotropic fireball. And well, I guess that isotropic fireball is actually rather far from what happens at LHC energies, because the dynamics in longitudinal direction is very different from transverse one. So this assumption of isotropic fireball, I don't know how well does it work, and maybe it might explain part of this failure at certain rapidity in the model. But that's rather a comment, so it's not really a question.
Yeah, but from the time you said, I think you asked for this. I don't know.
Yeah. Wait.
Because here for the rapidity side, yes, we have only the hydrodynamical model, so we don't have prediction from TAMU, but we are under our discussion. But
okay.
I agree that maybe it's a source of some issue.
Okay, thanks again, Robin, and we have to move on now. So next speaker is Leszek Kosarzewski. I hope I pronounced it properly, from Prague. So
it's Leszek.
Leszek. Okay. So yeah, right. Sorry. So you can project the slides.
Mm-hmm.
Okay. And if you like the camera, otherwise, as you wish, as you prefer. Okay. You can start.
Yes. So thank you for giving me this opportunity to present an overview of Upsilon production studies performed with the STAR experiment. So first of all, we celebrate 20 years of STAR, which is a nice anniversary. And for my presentation, I would like to study with introduction.
Sorry, Leszek, we see a gray box on the right.
Oh.
Can you try to close it?
Okay, yeah, maybe let me quickly. And you still see a gray box?
Yes. I think it's like a window from Zoom, could be.
Ah, yes, maybe that's right. Okay. Yes, sure.
Okay, now it's fine.
Yes,
Thank you.
yes.
Sorry
okay.
for the
I
interruption.
That's okay. Okay, so I would like to start with a short introduction, then describing the detectors used for Upsilon analysis, and after that I will show results of Upsilon production in PP collisions, P-gold collisions, and gold-gold collisions. Finally, showing projections for future runs with STAR, and ending with a summary. So in heavy ion collisions, quark gluon plasma can be created, then it evolves, and we can't observe it directly, so we need some kind of a probe, like Upsilon states, in order to study its properties. And as you know, Upsilon states are made of BB bar quarks, which are heavy and are created at the early stages of a collision. Next, they propagate through the medium, and at high temperature, they are expected to dissociate through Debye-like screening of color charges. And this is what we would like to study. So in STAR, for Quarkonium studies, we use a number of detectors. First of all, TPC for tracking and particle identification. And slightly outside, there is time of flight detector, which is used also for particle identification based on time of flight measurement. And in this analysis, we also use it for determination of charge particle multiplicity. Next, we have barrel electromagnetic calorimeter, which we use to trigger on high PT electrons and also for electron identification. And just outside of the STAR magnet, there is a muon telescope detector, which we use for muon identification, also using time of flight information. And muons have an advantage over electrons because of less Bremsstrahlung radiation. So in PP collisions, we measure Upsilon production in order to study the production mechanism of Quarkonium. And the bound state formation part is non-perturbative, but it has to go either through color singlet or color octet channels. Moreover, we can study Upsilon production as a function of charge particle multiplicity, especially high multiplicity events, and this allows us to gain insight into interesting interplay between hard and soft processes, as well as study of saturation effects or multiple parton interactions. In PP collisions, we've measured upsilons at 200 and at 500 GeV in the Dielectron channel. These are the signal distributions. It's very challenging to extract individual yields of individual upsilon states. But we do it by fitting invariant mass histograms using signal line shapes from a full star detector simulation. And these are for 1s, 2s, and 3s states. But we also have to describe the backgrounds. And this consists of combinatorial background. And on top of that, Drell-Yan and BB bar residual background. This data allowed us to obtain red PDT dependence of combined Upsilon states at 200 GeV and at 500 GeV. Here we also have separate Upsilon 1s, 2s, and 3s 3s cross sections. These are in fact new, and we can see that if we compare it to the models, we can see that at 200 GeV the data are slightly narrower than color evaporation model, while at 500 GeV they are flatter and well described by color evaporation model for inclusive Upsilon 1s production. On the other hand, CGC and NRQCD calculation for direct Upsilon 1s is slightly above the data. We've also calculated PT spectra of combined Upsilon states, 1s and 2s plus 3s. And they are also compared to models. And again, color evaporation model for inclusive 1s describes the data reasonably well. But CGC plus NRQCD model for direct Upsilon 1s production is slightly above the data, especially at low PT. We also calculated integrated cross-section for combined Upsilon states production, here shown as a function of collision energy. And these are started results at 200 GeV compared to previous published results, and results at 500 GeV. As you can see, the star data follow the world data trend and are consistent with color evaporation model calculation as well. Now, before I describe studies of multiplicity dependence, I would like to give an example of possible physics based on example of percolation model. So in PP collisions, when partons interact, they may form elongated strings of color field. And in high multiplicity PP collisions, we should have a high density of such strings, and they may overlap and interact. And so such interactions actually decrease yield of particles from soft processes, so decrease charged particle multiplicity, while yields of particles from hard processes are mostly unaffected. So we should see, in fact, an increase of yield from hard processes compared to soft processes. And this picture is similar to CGC. If you need more information, please go to backup. So these are the results of normalized Upsilon yield shown versus normalized charge particle multiplicity. Star data are shown as blue points and red points at high PT. We can see that if we compare it to JPSI and other Upsilon data, both at RIC and LHC, we see that there is a similar trend across all experiments. And if we compare that to the models, we can see that the data are well described by PTA 8 and string percolation model calculations reproduce the trend in the data. And CGC and saturation model also describes the data, however, within large uncertainties. So this suggests that upsilons may be produced in multiple parton interactions, or that there are saturation effects happening at high multiplicity events. Now moving on to P-gold collisions. In such collisions, we can study cold nuclear matter effects, which for upsilons can be Commover interactions. However, for upsilon 1s, these are expected to be small. Also, the effect of nuclear absorption can be studied. In addition to effect of nuclear PDFs, which consists of shadowing and anti-shadowing, which either decrease or increase yield of gluons available for BB bar production. And all these effects can be studied by measuring nuclear modification factor. So these are star results in P-gold collisions at 200 GeV. That's the signal, upsilon signal. And out of this data, we've calculated RAA, nuclear modification factor, versus rapidity for combined upsilon states. These are shown as red points. And you can see that we now have around 50% smaller statistical uncertainty compared to previous star measurements. And in the data, we see an indication of suppression of combined upsilon states. Now moving on to heavy ion collisions. In such collisions, we can study QGP effects. However, cold nuclear matter effects may also play a role. But the most important effect we would like to study is this anomalous suppression at high temperature in QGP due to the Debye-like screening of color charges. And since we have many upsilon states, each state can dissociate at a different temperature, which provides us an estimate of the temperature reached in a collision. And we should see a sequential suppression pattern. But this is a bit more complicated because of feed down, which also gets modified. But the good point is that in case of upsilons, regeneration should be negligible, especially at RIC energies. So in gold-gold collisions at 200 GeV, we have data. We have upsilon data measured both in Dielectron and dimuon channels. The results are consistent, so we combined RAA for better precision. And here you can see RAA of upsilon 1s versus number of participants compared to CMS data. The results are similar both at RIC and LHC, and that's despite higher medium temperature reached at LHC. And this could be due to suppression of excited states, maybe some effect of regeneration, which should be larger at LHC. Also, cold nuclear matter effects may still play a role, and these need better constraints. We also have RAA for Upsilon 2s plus 3s compared to CMS results. And there's an indication of smaller suppression at RIC than at LHC. If we compare our data to the models, also versus number of participants, here are the calculations for Rotkopf model for Upsilon 1s and 2s plus 3s. The data are also compared to RAPS model. As you can see, both models agree with the start data. Both models assume a hydrodynamic medium. However, Rotkopf's model doesn't include regeneration or cold nuclear matter effects, while RAPS model includes these effects. And you can see that Rotkopf's model underestimates RAA of 2s plus 3s at 30 to 60% centrality. We also have plans for the future in STAR. We plan to install a forward tracking system to have tracking at high pseudo-rapidity, complemented with both hadronic and electromagnetic calorimeters. There's also ITPC, an improved TPC, which is already running, so it provides improved momentum resolution. We also plan to have high integrated luminosity runs we used for precision studies of Quarkonium production, many more. So for multiplicity dependence, we should get for Quarkonium studies versus multiplicity, we should get 750 inverse picobarn in the Dielectron channel and 370 picobarn in the dimuon channel. And you can see that for JPSI, it provides precise results. Also for Upsilon versus normalized multiplicity. And it should be possible to discriminate, with this data, it should be possible to discriminate between different models. We also plan heavy ion runs after 2023. This is the simulated signal for Upsilon 1s and 2s, which should provide us with really high precision measurement of RAA of Upsilon states. So we should get RAA for Upsilon 1s and 2s states separated versus centrality and versus PT. Now moving on to my summary. We've measured Upsilon production in PP collisions at 200 and 500 GeV. The data of inclusive 1s state are reasonably described by color evaporation model, while overestimated by CGC plus NRQCD model. Rapidity spectra are flatter at 500 GeV. We see similar trends for both JPSI and Upsilon at RIC and LHC. And in the future, we should be able to discriminate between the models. In P-gold collisions, we see indication of combined Upsilon states suppression. And on the other hand, in the gold-gold collision, we measured Upsilon RAA in both dielectron and dimuon channels, which are combined for better precision. Upsilon 1s shows similar suppression both at RIC and LHC. We also see stronger suppression of Upsilon 2s plus 3s than 1s, especially in central collisions, which is an indication of sequential suppression. And also there's a small hint of smaller Upsilon 2s plus 3s suppression done at LHC. And all these results are consistent with model calculations. And after 2023, we should be able to have high precision measurements of RAA versus PT and centrality. So thank you for your attention, and let me advertise you other STAR presentations at ICHEP. So thank you very much.
Thanks a lot, Leszek, for this very clear talk. So it's time for questions now. We have time for one question or two quick questions. So I don't see raised hands. Let me check Matamos channel. So I have a question about slide 7.
Mm-hmm.
So you show this trend, yes, with a sort of depletion at mid rapidity. Is this consistent? The figure on the right, is it consistent with the trend that you observe on the left? I mean, I'm a bit surprised by this dip that you see.
Yes. So I checked that, and this is actually on 2 sigma level significance. It's not that much. I believe it's just a fluctuation. So in the signal, we really do observe Upsilon 3s at mid rapidity. Yes. So, but again, it's not that significant.
Okay, and the sum of the free states and the Upsilon 1s look consistent with the result that you showed, with the previous results at lower energy, where it seemed that there were a more marked trend with rapidity.
So what do you mean? Could you say that again?
So if I look at the left figure, it seems that the trend is is more pronounced with rapidity. So if I look at the red and green point here, it seems a bit different.
Yes. So of course there is a difference. Because of collision energy, the rapidity distribution just gets more spread out, and that's why it's more flat at 500 compared to 200.
Okay. Okay, and we have to move on. So thanks a lot again, Leszek.
Oh, thank you.
So next speaker is Alexandra from Oslo. Alexandra Neagu.
Yeah, it's Neagu. But
Neagu,
for the introduction.
Yes.
Yeah, so can I start? Do you see the slides?
Yes, can you also, well, if you want, you can use the camera and share yourself.
Yeah, it's on. So you should also see me. Okay. So today I'm going to present you the latest Alice measurement of charmonium production in lead-lead and in pellet collisions. But first I want to start with a short physics motivation before I move to the results section. So as we know, charmonium are bound states of CC bar pairs. And in case of vacuum, the quark-antiquark pair potential is described by the Coronal potential that has two components, a Coulomb-like term and a linear term. But then if the hot and dense medium is created, the potential is going to be modified, and it will have the form of a Yukawa-like potential that where the Coulomb term is going to be screened. And also it will depend on the quarkonium binding radius and also on the device screening length, which is proportional with one of the temperature. If lambda d is smaller than the binding radius, then we are going to have melting of the quarkonium states. And also the screening effect is sensitive to the temperature, but it also depends on the quarkonium binding energy and also on the binding radius that will cause a sequential melting of the different quarkonium states. And here in the right plot, we can see the state-of-art lattice QCD calculations that assess the modification of the complex heavy quark potential in thermal bath. So here we have the real part and also the imaginary part of the potential. In addition, at DLHC, due to the larger CC bar pair production, it is expected an enhancement of the charmonium production due to the stronger regeneration effect. So we will have this additional effect besides the suppression. So let me summarize my physics motivation. So we can consider charmonium production as a useful tool to probe the in-medium QCD force, and also it can give information about the medium transfer properties. But it is also important to look in other collision systems like PLED to test for possible conuclear matter effects, but also to look if there is any sign of collective motion also in this kind of collision systems. In ELIS, we are capable to measure charmonium down to PT equal to 0 into rapidity regions. So we can measure the charmonium at mid-rapidity and the JEP size reconstructed in the dielectron decay channel. Also, it is possible to separate between prompt and non-prompt components, the non-prompt being a proxy for open beauty hadrons. Then the different charmonium states can be also reconstructed at photon rapidity in the muon decay channel using the muon spectrometer. For those maybe that connected now, if you want to see the recent Bottomonium results, you can have a look at Robin's presentation. Now I will move to the recent results in lead-lead collisions. And whenever you are going to see the label new, it means that the results were published for this summer. And now moving to the results, one of the observable that is used to quantify the in-medium modification of the charmonium production is the nuclear modification factor, which is the ratio between the charmonium yields in nucleus-nucleus to the ones in PP, scaled by the number of nucleon-nucleon collisions. And here in the left plot, we can see the JEP psi RAA as a function of the charge particle density at different energies. So we have the measurements from ALICE at 2.76 in green and at 5 TeV in red. And the results at 5 TeV were obtained with the data collected in 2018. And we can see that there is a similar suppression between these two energies. But then when we are looking at and comparing the JEP psi RAA to the one at lower energies, especially, and here we have the RAA in gold at 200 GeV. We see that the suppression is stronger at RIC compared to LHC, even though the energy density is larger at LHC compared to RIC, and this could point to the regeneration scenario. Now, moving to the model comparison for the JEP psi RAA, here we have different models, and we see that there is an agreement with the data with the models that include the charm quark regeneration. So in this case, we have the transfer model where there is a continuous dissociation and regeneration of the charmonium states in the quark-gluon plasma and at hadronic phase. Then we also have the statistical hadronization model where all the charm particles are generated at chemical freeze-out. But there is also the Comover interaction model where the suppression is due to the interaction with the co-moving medium, but they also include a regeneration component. So we can see here the results for mid and also for the forward in the right plot. Now, moving to more differential measurements, here we have the JEPSI RAA as a function of PT for different rapidity regions. So we have the mid rapidity results in magenta and different forward rapidity intervals in red, blue, and green. And it can be observed that for PT less than 5 GeV/c, the JEPSI suppression depends on the rapidity, having a larger RAA for mid compared to forward region. And this can be explained in the regeneration scenario by the fact that the charm cross-section is higher at the mid rapidity. Then if we move to the high PT region, we see that the suppression is stronger compared to the low PT region, but it doesn't have a rapidity dependence. And when we are comparing the JEPSI RAA with the models for mid rapidity in the left and forward rapidity results on the right, we see that the transport model is able to describe the data over the whole PT range, and this applies also for both rapidity intervals, while the statistical hadronization model is able to describe the data only qualitatively in the low PT region. There is also another interesting result, and this is related to the JEPSI polarization, and this was measured at forward rapidity. And this is the first measurement of the JEPSI polarization that has been ever made in lead-lead collisions. And the study of polarization can be used as a tool to test the current knowledge of the QCD. And experimentally, this can be measured by studying the anisotropy of the angular distribution of the decay products, and this can be expressed with a two-dimensional distribution as it is shown here, and this depends on the polarization parameter lambda theta, lambda phi, and lambda theta phi. And in the case where all these three parameters are 0, then there is no polarization, while when lambda theta has values of -1 or +1, then as you can also see here, we are going to have a longitudinal or transverse polarization. And if we look in the left plot where we have the polarization parameter as a function of PT for the helicity reference frame and also for Collins super reference frame, we see that in the low PT region for lambda theta, there are a deviation of up to 2 sigma, and this could point and also can be a hint of non-zero polarization in lead-lead collisions. Now, moving to another observable that can be used to study the properties of the QGP, and this is anisotropic flow. So in this case, the particle azimuthal distribution can be expressed in terms of a Fourier series with respect to the symmetry planes. And the Vn coefficients, also known as Fourier coefficients, quantify the event anisotropy. So we are going to have V2 as elliptic flow and V3 as triangular flow. And if we look in the right plot where we have the V2 as a function of PT for the D mesons for two different centrality classes, we see that there is a large D meson V2 that was measured. And this could point to the fact that the charm quark thermalizes in the quark-gluon plasma. And now the question that arises is that if also the JEPSI is going to inherit any of the charm quark flow. And now if we are looking at the V2 as a function of PT, we see that we have, of the JEPSI, we see that we have a significant positive JEPSI V2, and also the full run to statistics allowed us to do a more precise measurement and also to go higher in PT up to 15 GeV/c. And if we look in the low PT region, we see that we have a large V2, and this can be described by the transfer model, and this could be explained by the JEPSI production through regeneration. While if we look in the high PT region for PT greater than 5 GeV over C, we see that the V2 remains high, but it's underestimated by the transport model, which means that there is a missing mechanism that is not taken into account. Because we saw that the transport model is able to describe the RAA over the whole PT region, while it cannot do the same for elliptic flow. Another study that was performed is related to the so-called event chip engineering. And with this technique, we can select events based on the initial geometry. And what we do in this case is to apply some selection on the so-called reduced flow vector. And in a given centrality class, we can select events that have more like an elliptical geometry or more like a spherical geometry. And now if we are looking in the left plot where we have the V2 as a function of PT for these Q2 classes considered, and also for the unbiased sample. And in this case, unbiased sample means that no cut and no selection was applied. We see that we have an ordering with the Q2 class. It is also important to look at the ratio between these Q2 classes and the unbiased sample. And here we have this ratio for the JEP psi and also for the muons. And it can be clearly observed that also the JEP psi is sensitive to this event shape variation, pointing to the fact that the charm quark flows with the bottom. Now moving to more differential measurements. So here we have the JEP psi V2 compared to the D mesons and also with the pions in different centrality classes. In the low PT region, we can see a clear mass ordering with the V2 for the pions being the largest. And this can be better observed in semi-central collisions. While if we go to higher PT, we see that the V2 for pions and D mesons and JEP psi is almost the same, and they align on the same curve. And this could put further constraints to the in medium energy loss models. It was also possible to measure now with reduced statistical errors the JEP psi V2 at mid rapidity, and we measured it with a 3 sigma significance, and we can see that, and here are the points in magenta, and we can see that the measurements between mid and forward rapidity are compatible. Now moving to the triangular flow, we also measured the JEP psi V3 at the forward rapidity, and we observed that we have a positive JEP psi V3, which has a weak centrality dependence. And also here you can see the JEP psi V3 compared to the D mesons and also pions. And as in the case of V2, in the low PT region, we can also see the mass hierarchy. There was another study that was performed, and this is related to the number of number of constituents quark scaling. And what we did in this case was to try to extend the quark coalescence picture and to describe the D meson flow in terms of 2 flow components, one for the light quark and one for the charm quark. And we can express it as you can see here. And the flow for the light quark was obtained from the flow of the pions, while for the charm quark, it was obtained from the flow of the JEP psi. But there were also some assumptions that were made regarding the PT sharing between the constituent quarks in the D mesons. And here is the PT sharing that we considered. And here you can see the V2 as a function of PT, where we apply this scaling. And we see that when we consider a roughly equal PT sharing, this scaling works. And we can describe the D meson flow. We can also look in other centrality classes. And here in the lower panel, we have the semi-central collisions and we go up to central collisions, and we have in the left part the V2 and V3 is on the right part, and we can see that this scaling works for both V2 and V3 over the entire PT range and also for all centrality classes. Now I'm going to move to the results in PLED. And as I said in the beginning, it is important to look in also in PLED to test for possible cold nuclear matter effects or to see if there is any sign of collective motion. And in this case, we have 3 rapidity regions available. We have the forward, the mid, and the backward. And now moving to the results, first I will start with the inclusive JEP-Psi RP-LED as a function of rapidity in the center of mass frame. And here we can see that the backward and the mid rapidity results are compatible with unity, while the forward results we can see a large suppression. Also, we have comparison of the data with different models, and there is an agreement with these models, but the fact is that these models include have different approaches. So we have models that include initial state effects. So we have shadowing or color glass condensate, but there are also energy loss. We have also an energy loss model. And in addition, there are also available models that include final state effects like the microscopic transport or the comovers. As I said in the beginning, at mid rapidity, we can also separate between prompt and non-prompt JEP-Psi. And here we have the RP-LED as a function of PT for non-prompt on the left and for prompt on the right. In the case of non-prompt, we have a comparison of the ALICE results with the CMS results, and we see that there is a slight tension between the results in the intermediate PT region, but we also have available a model prediction from EPPS16, and we see that the model calculations are in agreement with the data. Now moving to the prompt component, we see that the suppression is mostly concentrated in the low PT region. And we also have here different models available. We have models that include shadowing or color glass condensate and also energy loss. And the data are consistent with the model's prediction. Now moving to other charmonium states, and now I'm going to present the Psi2S results in PLED. So here we have the RP-LED as a function of rapidity for the backward region and also for the forward region, and the Psi2S results are compared to the JEP-Psi results. And we can see that in the backward region, the Psi2S is more suppressed compared to the JEP-Psi, and also the models in this region that include only initial state effect cannot explain the difference between these two. While if we move and we have a look in the right plot, we see that the models that include final state effect can explain the difference between Psi2S and JEP-Psi. So we have the comovers, but there is also the CGC plus ICHEP calculations that can also differentiate between the two states. And if we look now at the RP-LED as a function of PT, for Psi2S and JEP-Psi, we can better see that Psi2S is more suppressed than the JEP-Psi for both rapidity ranges. So we have here the backward rapidity, and on the right is the forward rapidity. And also we have calculations available for forward rapidity, and we can see that there is an agreement with the CGC-based calculation for the forward. And this brings me to the last result that I'm going to present, and this is the V2 as a function of PT for the backward and also for the forward region, and the results are also compared to the JEP-Psi results in LED-LED. And we can see that for PT less than 3 GeV, the V2 is consistent with 0, while for PT greater than 3 GeV over C, we see a significant positive V2 also in PLED. And also, if we look and compare it to the LED results, we see that we have almost the same amplitude. But similar observations were also made in PLED for other species. So we had similar observation for light flavor and open charm hadrons. And this brings me to my conclusions. So what I presented today were the latest ALICE measurement of charmonium production in LED and in PLED. Now in LED collisions, we saw that at low PT, the JEP-Psi production is predominantly through regeneration, while when we looked at high PT, we saw that there is a strong JEP-Psi suppression that does not depend on rapidity. Also, we saw that we have significant JEP-Psi V2 that suggests that the charm quark thermalizes in the QGP. Also, we could extend the quark coalescence picture, and the conclusion from this is that the JEP-Psi in the D meson are described assuming a common underlying charm quark flow. And now moving to PLED collisions, we saw that there is a larger suppression for Psi2S compared to the JEP-Psi, and also the Psi2S suppression cannot be explained only with initial state effects alone or with energy loss effects. And there were then we also observed significant JEP-Psi V2 also in the case of PLED. And thank you for your attention.
Thank you, Alexandra, for the very nice talk and lots of results. So we have time for one question. So participant, please raise your hand. Yuri.
Yes, so I have a comment and a question actually. So the comment is to slide 12 when you compare the PT dependence to the statistical hadronization model. So the thing is, the statistical hadronization at large PT, it not only doesn't work for the RIA, I mean, it doesn't work for anything, because after few GeV, you basically don't expect that any heavy energetic objects are produced in a statistical way from the freeze out. I mean, it's just not realistic. So that's coming from hard processes. That was rather a comment, but I also have a question to slide 19. When you basically, I mean, there's this argument of NCQ scaling and the argument of adding the elliptic flows of different quarks. So naively, I would say that, for example, the transverse momentum is kind of additive quantity. So you can add transverse momenta to get the transverse momentum of the composite object. But the elliptic flow, I mean, it's like RIA. It's different type of quantities. So it's not obvious why you should add elliptic flows of different quarks. So are there any simple arguments why the elliptic flows are simply added to form the elliptic flow of D meson?
I mean, in this case, what we try to do with this, because we know that at LAC and also at RIG, we had this scaling where we could express in the hadronization scenario, we could express the V2 in terms of the constituent quark. But I guess in this case, I mean, why we add it, I mean, in order to have a bound state, I'm guessing then we should have a common. I mean, we should have a contribution from both of them, right? But when we do this assumption, I mean, when we do this assumption that the V2 of the D meson is just, I mean, is a sum of the V2 of the light quark and the charm quark, we see that this assumption works.
Yeah, okay, so this is a very interesting discussion indeed, and you can keep discussing on the Matamos channel, or we can also come back to this during the coffee break. Now we have to move on now, so thanks again, Alexandra. And the last speaker before the coffee break is Jiayin. So Jiayin, you can share your slides and turn on your camera if you wish.
Okay, can you hear me now?
Yes.
Okay, great. And can you see my slide?
Yes, can you go full screen? Yes, perfect. Okay, you can start.
Okay, great. Okay, so I'm going to talk about Quarkonia and open heavy-flavour production in P-like collisions at the ICHEP collaboration. So here is a list of the recent open heavy-flavour and Quarkonia results we have at the ICHEP. So we have two modes. One is the collider mode, and the other is the fixed target mode. So the results in the collider mode, we have for open heavy-flavour, the prompt D0 and the lambda C, and also some B hadrons as well. For the Quarkonia, we have J psi and Upsilon. And for the fixed target mode, we have some charm productions in P helium and P argon collisions. And so firstly, heavy-flavour is interesting because they are produced in the early stage of the collision, so they can experience the whole time space evolution of the heavy ion collisions. And so they are sensitive probes to study the properties of the QGP created in A collisions. And we already know from measurements that they interact strongly with the medium. So they lost a lot of energy in the medium. And also the sequential melting of the Quarkonia states can be used to investigate the medium temperature. And also baryon to meson ratio in charm and the bottom sector can probe the hadronization in the QGP. So that's also important observable. And if we assume that the QGP is not important in PA collisions, then we can use the heavy-flavour in PA collisions to provide a baseline measurement to disentangle the cold nuclear matter effects from the effects of the hot and dense medium. And then the LCB is an excellent detector that's well suited to such measurements because it can measure heavy-flavour down to very low PT, and also it has excellent vertex resolution, so it can separate the prompt and the bottom decay components. And for the cold nuclear matter effects that we interested, the most important is the initial state effect that can be described by the modification of nuclear PDF, or alternatively can be described by the ground saturation scenario. There are other effects like multiple scattering of partons in the nucleus. And also for Quarkonias, the final state effect, like the commuers, are also could be important. And so for the P-like dataset in the IHCB, we have two datasets. One is the 5 TeV, a smaller dataset, and another big one at 8 TeV. And so because the LCB detector is single-armed, so we have two configurations. In the forward configuration, the proton beam goes into the detector, and we have a center of mass coverage of rapidity between 1.5 and 4. And for the backward configuration, the light beam goes into the detector, so it covers the rapidity between -5 and to -2.5. So our first most recent result from the open heavy-flavour is the double charm production at 8 TeV in the p-like collisions. So this is the first double charm measurement in heavy ion collisions. So for single parton scattering, we know this parton from one incoming nuclei and collide with another parton from the other incoming nuclei. But for double parton scattering, there are two partons from the incoming nuclei and collide with the other two partons from the other incoming nuclei. And so normally the DPS is power suppressed compared to the SPS, but theoretical calculations show that the DPS can be significantly enhanced in heavy ion collisions, and because the double parton can come from different nucleons in heavy ion collisions. So the prediction is that there would be a factor of 3 enhancement for the DPS in p-like collisions. So we can investigate this enhancement by looking at charm pairs, and we can divide the charm pairs into Lexan pair. For example, the D0-D0 pair that has the same quark content. So we expect those Lexan pairs has a large contribution from the DPS, and we assume those Lexan pairs are uncorrelated if there's no parton level correlation. And on the other hand, there are opposite sign pairs like D0-D0 bar, and we know they are mostly from the CC bar pairs from the SPS. So the plot here shows the, for example, signal from the D0-D0 pair, and you see the mass distributions of the two D0s. And we can look at the kinematic distributions of those D0 double charm pairs. So the left plot is the invariant mass of the charm pairs, and the right one is the Lexan pair, and the blue one is the opposite sign pairs. So there seems to be a slight difference between the two distributions, and the Lexan pairs seem to have a harder distribution than the opposite sign pairs. And also you can see the purple dotted line here, and that is the PCR8 calculation of the unlike sign, and it's in nice agreement with the blue points. And on the right is the DeFi distribution of the pairs. So for the unlexan pairs, you see the blue, there's a clear near side peak at around 0, which we expected. Also, the PCR simulation shows that too, but at a lower value. And the right Lexan pairs is consistent with flight. And this is what we expected. And this is consistent with the assumption that the Lexan has a large contribution from the DPS. So we look at the ratio of the Lexan pairs over the opposite sign pairs in the left plot here. And the orange line here is the LCB measured value from PP collisions. So we see that in P-like collisions, there's a clear enhancement of the Lexan pairs shown by this ratio. And so if we assume all the Lexans are from the DPS, we can use this formula here, and we calculate the DPS effective cross-section. And that's the show in the right plot. The shaded line here is PP extrapolation assuming that the DPS is enhanced by a factor of 3, and this shaded band is consistent with our measurements. And so we say that we confirm the expectation that the DPS is enhanced by a factor of 3 in P-like collisions compared to PP. And if we look closely, there's some details like the J-side pairs has a lower sigma, effective sigma than the DD pairs. And also in the this cross-section is higher in the forward rapidity and lower in the backward rapidity, that seem to indicate the DPS is enhanced more in the backward compared to the forward. So all those details are interesting, and we can investigate with future measurements. So another new result from the LCV is the prompt D0 production. And we use the D0 to K pi decay chain to reconstruct the D0. And we use the impact parameter distribution to separate the prompt and the from B distributions. And the plots below are the forward-backward ratio RFB as a function of PT and rapidity. And what is interesting is for the PT, at lower PT, the RFB is consistent with the our previous measurement at 5 TeV, and also the color bands, which are the NPDF calculations. But the red points rise faster than the 5 TeV points, and also the NPDF, and reach almost 1 at PT at 10. So you can also see that the systematic uncertainty is much larger than the statistical uncertainty here in these points. So we are working on reducing the systematic uncertainty here, and also working on to push this measurement up to higher PT beyond 10, so that this trend, this rising trend, can be more clear. We also have other open charm measurement and at 5 TeV. So the left plot here shows the nuclear matter modification factor RP light for the prompt D0. So the RP light is at about 0.7 in the forward, and it's at about 1 in the backward. There's a significant suppression in the forward rapidity. And the result is very precise and is already used by theorists to constrain the NPDF in very low X region. We also look at the prompt lambda C to D0 ratio. And in the forward and the backward, the ratio are about the same. They are at about 0.3, which is consistent with our lambda C to D0 ratio in the PP collisions, also consistent with the calculations shown in the colored band. But this ratio is lower than the Alice measurement in mid rapidity. So this could be effect of rapidity dependence or something else. So that's also an interesting point that we need to investigate. And we also have nice result from B hadrons, open Bolton hadrons, and using fully reconstructed final states. So the plots here shows the RP light for B plus as a function of PT and rapidity in the forward rapidity and the backward. We see that in the forward, the RP light is at about 0.8, and there's a separation slightly less than the charm case, and in the backward, the points are at 1. And we also look at the particle ratio lambda B to B0 here, that's shown in the blue. So the forward and the backward are also about the same at 0.4, which is consistent with the LHCb measurement from PP. And we also see this shape with PT. That rises first and then decreases at higher PT. That's also the similar shape in the charm case. Now we come to Quarkonia. The prompt JSA are reconstructed through the dimuon channel, and the prompt and from B components are separated from the pseudo-proper decay type. And for the RP light as a function of PT and rapidity. So in the forward, there's a significant suppression for the prompt JSA. At 0 PT starts from 0.6 and rise up to 1. And in the backward, the points are more closer to 1. And they are compared to 3 different NPDFs, as well as the CGC here in yellow and the energy loss model in green, and they are consistent with all those models. And this is the Upsilon result from the LCB. You can see our Upsilon signals. There are 3 very nicely separated signals, and we also have pretty nice statistics for the Upsilons. And so this is the RP light for the Upsilon 1s state and 2s state. In the forward rapidity, the 1s and the 2s states has the same level of suppression. The points are about the same. But for the backward rapidity, you see the 2s is significantly below the NPDF and is also below the 1s points. And these points can be described by the NPDF plus Comover model. So we look at the relative suppressions. And so to look at the double ratio, so this is the double ratio is the relative suppression of the NS state to the 1S state in P-light compared to PP. This is 2S to 1S, and this is the 3S to 1S. In the forward, they are similar, but in the backward, the 3S has significantly more suppression. So as the initial state effects are cancelled, so that points to final state effects. And we use a Comover model and show in the green, and that's consistent with the data shown here. And the LCB is also unique in that we have this active fixed target physics program. So we use the smoke that is originally a device to measure the luminosity. So we found that we can inject a small amount of noble gas into the HCB beam close to the interaction points, like here. And the gas can be used as a fixed target, and that allows P gas and ion gas collisions. And so the resulting energy would be between 70 to 110 GeV. That's nicely between the SPIs and the RIC energy. So in this configuration, the kinematic coverage would be the mid rapidity to the backward rapidity. And that allows us to access the anti-shadowing region in the NPDF. Also, we can test the intrinsic charm content in the nucleus that's shown here. So one of our first fixed target result is the charm production in p-helium collisions. And this is J psi and D0 signals. And we measured the J psi and CC bar total cross section that's shown in the right here. We have very small error bars and they are consistent with the yellow band from the theory and also other previous measurements. And so this is also the first CC bar measurement in this energy region. And interesting result from this measurement is that if you look at the most backward beam from the D0 invariant mass or invariant yield, and so this most backward beam corresponds to the Bilken X in here. And so we can see if we can observe intrinsic charm content in this beam. So we can compare to the theoretical calculation shown in the green here. That's the Halleck-Onia calculation with the NPDF without the charm, without any intrinsic charm contribution, and we don't see any enhancement. So we conclude that we do not see evidence of strong intrinsic charm from this measurement. And we also have some very interesting upcoming results. So hopefully in the near future we can see them. That includes some high statistic D0 and lambda C measurements, and not D0, sorry, D plus and D sub S and lambda C with very high statistics. Also, we are having a first measurement of KC1 and KC2 states coming out very soon. So they could be very interesting. Now, coming to our conclusions, we measured open heavy-flavour hadrons in P-light collisions, and we found that the DPS, the double parton scattering is enhanced by a factor of 3 compared to PP collisions. And looking at the prompt D0 method, we can measure it precisely down to 0 pt, and we found a significant suppression in the forward rapidity. And we measured the prompt lambda c to D0 ratio. It's at about 0.3 and consistent with PP and the theoretical calculations, but lower than the ALICE result. We measured the B hadrons and found a smaller relative suppression in the forward rapidity, and the lambda B to B0 ratio is at 0.4. For the Quarkonia, we have precise result from JSI that confirm the relative suppression similar to the D0 case. And for the Upsilon Ni states, we've seen relative suppression of the 3 Ni states in the backward data. And we have measured the charm production with the fixed target mode, SMO. And from that measurement, we see no evidence of strong intrinsic charm contributions. And we'll have some very interesting upcoming results. For example, the other charm methods with high statistics and our first Chi-C production in PLED datasets. And that is all. Thank you very much.
Thanks a lot, Jiayin, for the very nice talk and all the results. So it's time for question now. So I don't see hands raised. Let me check the Mattermost channel. Okay. So I have a question concerning the double parton scattering that you discussed at the beginning. So there, what is not fully clear to me is, so you do this measurement of a double D meson production, basically. But of course, indeed, as you also said, one expects that you may have several D, well, you have events in which you can produce several D just because also you have more nucleon-nucleon collisions than PP. But double parton scattering somehow could go a bit beyond this in the sense that you may expect also interferences in the production of two C-quark pairs, and this may produce some kinematic effect. So in what you showed so far, if I got it properly, there is not a search for this type of effect. So it could be that what you see is just independent overlap of independent scatterings. Is it correct? And what are the plans for trying to go a bit beyond this?
For now, I think there's no assumption from other effect aside from the just the combination, the calculations that the double partons can come from different nucleons, and that leads to an enhancement in the heavy ion collisions. So for now, there's no other assumptions yet.
Okay, thank you. We may discuss it also on the Mattermost channel a bit more. Okay. So I don't see other questions. So thanks a lot, Jiayin. So now we have the coffee break. We have only 5 minutes left. We are a bit late. So we resume at 10:36. And in the meantime, so we speakers of next session that haven't yet tested their system before the starting can test it now. So I see Chiara Pinto. Can you hear me?
Yeah.
Okay.
Yes.
So can you try to share your slides? Turn on your camera if you want, of course, and
yes, thank you.
Yeah.
See. Okay, can you see the slides, right?
Yes. Can you try to go full screen?
Yes. Okay, that works.
Very good. Okay. And the camera, I mean, do you plan to turn it on or not?
Yes, I can. Yes, yes.
Okay. So
wait, I have to. Okay. Yeah. Okay.
Okay. Very good. Thank you. So, Andrii, Are you connected? Yes.
Hello. Yeah.
Hello. Okay, very good. Perfect.
Okay.
Okay. Then Sergei already tried it before. Luke, are you connected?
Yes, hello.
Yes, hi.
Wait
So,
a second.
Let me share.
Yes,
I
Andrii, you should stop sharing, please. Okay. Luke, so, okay, perfect. And Lukas, you already tested before. Xinye, so last but not least.
Okay, can you hear me?
Try? Yes. So Luke, stop sharing. Okay.
Can you see
Very
me now?
good. Yes.
Okay.
Can you try to share the slides?
Okay. Wait a moment.
Okay. Can you go full screen?
Yes.
Perfect.
No. Okay.
Okay. Like this, it's perfect. Okay. Okay. So we have 2 minutes left before we start again. So see you in a while. Okay, so we resume the heavy ion session. So Andrii, can you start?
Yes.
Okay.
Do you see the slides? Yeah.
Yes. Okay. So I'll notify writing you 5 when you have 5 minutes left.
Okay.
And okay, so let me remind the participants that they can ask questions at the end of the talks by raising their hands, or they can also profit of the Mattermost channel, writing question there, and there they can also keep on discussing with the speakers and the other participants, of course. Okay, Andrii, so you can start.
Okay, hello everybody. So my talk is about KC-1 3872 production in proton-proton collisions with particle multiplicity, and it is on behalf of the LHCb collaboration. So I start with this well-known picture of charmonium spectroscopy. So you can see on this picture on black measured charmonium states, and on red it's prediction from potential Godfrey-Isgur model. And you can see that already here, the potential model qualitatively well describes the charmonium spectrum. For more precise spectroscopy results, you can go to lattice QCD and obtain more precise values for mass widths of the states. There are several important thresholds for charmonium. The first is DD bar. And the states that are close to it and above it are usually much broader than the ones below because they can decay into new channel, opened threshold. For more LHCb results on conventional Quarkonia, I refer you to talk by Zhu. Once some state was discovered experimentally and it doesn't fit into the prediction, it becomes a candidate of exotic hadron. So more than 20 so-called charmonium-like states were already observed, and they need to be interpreted. So you can see here, for example, in blue is shown these charmonium-like states. Then in magenta, you can see the charged exotic candidates. There are also pentaquarks. But for more results on exotic states, please see the talk by Daniel Johnson, also from LHCb. So for these exotic states, there are many possible interpretations. If they are really hadrons, then there are possibilities that they are meson anti-meson molecules, compact tetraquark or hadrocharmonium or adjoint charmonium. But of course, some of them might be some dynamical rescattering effects or cusps or so on. Then KC-1 3872, formerly called X3872, was observed almost 20 years ago by Bell in J-psi pi spectrum. So you can see peak from Bell here. Then this discovery was followed by measurements at Babar, CDF, and LHC experiments, and it is the exotic hadron candidate. It is very narrow, unlikely to many other exotic states, that disfavors pure charmonium interpretation because the charmonium states in that region are expected to be broad. Then it is very close to DD star threshold, such that you see for now experimentally the experimental uncertainty is larger than the difference between its KC-1 3872 mass and the threshold value. So the possible interpretation of this state that it can be weakly bound hadron molecule, but other models are still in the game, like compact tetraquark, mixed state, etc. So the nature of this state has to be understood. And starting from here, I focus mainly on LHCb contribution. So LHCb established quantum numbers of KC-1 3872 to be 1++. So you can see on this right picture how the last surviving alternative hypothesis was rejected. It was 2- hypothesis, rejected more than at 8 sigma level. Then there is a very recent precise line shape measurement which will be covered in talk by Daniel again. There is a set of measurements and searches on Chi-13872 decays. Particularly, what was important is the evidence of its decay to Psi2S gamma, where the branching fraction was found to be much bigger, much larger than expected from pure molecular model, meaning that pure molecular interpretation was rejected by this. There are also many studies and discoveries of B hadron decays to Chi-13872, and for recent results of B decays to charmonium, you can see talk by Lian. Then another powerful tool to study nature of the state is to measure its prompt production, to study its QCD properties. So the first prompt production measurement at LHCb was done, where the cross-section times the branching fraction of Chi-13872 to J psi pi pi was measured. It was only absolute measurement. So the differential production cross-section still to be measured at LHCb. But then there is also recent prompt production measurement by Atlas. You can see the results here. So you can see the PT differential cross-section here. Black is data points, and pink is the theory prediction, where the theory assumes that Chi-13872 is a mixture of Chi-1 2p state and DD star molecule. So it shows a good agreement, but this prediction was tuned. And then the next thing that can help in understanding the nature of the state is production in medium. By studying in medium effects. So in this talk, I will talk about the dependence of production on event multiplicity in proton-proton collisions, but then you can go to measure nuclear modification factors in heavy ion collisions. So promptly produced quark pairs, they can dissociate due to interactions with surrounding activity or medium. And then for results on conventional charmonium, you just saw a talk by Jiayin. And also please see a talk by Julia about also heavy ion physics. Then in medium effects are expected to be enhanced for Chi-13872 if it has large radius, which is likely the case if it is a molecular state, because molecular state is expected to have a radius about 7 Fermi, which is much bigger than any charmonium state. So it's going to be a powerful test if we compare the effects in medium effects with respect to ones observed for charmonium states, and particularly Psi2S, because it is very well known and very close charmonium state to Chi-13872. So this brings me to the measurement, which is reported in this conference note. So this is a preliminary result. Then I start with the LHCb detector. So LHCb detector is a forward detector designed to study forward physics in beauty and charm sectors. Compared to B factories in the context of the studies of Chi-13872, at LHCb we have much larger heavy quark production cross sections compared to B factories. So you can see typical values here. And of course, there is no prompt production at B factories. Then if we go into details about the detector, a very important part of the detector is VELO, is a vertex detector that aims at reconstructing proton-proton collision vertices and also B decay vertices. What is important for this analysis is that the number of tracks observed in VELO is used as a proxy to event multiplicity. Then together with VELO, there is also tracking stations that help to reconstruct the momentum of charged particles. The tracking system, there is a part located downstream of the magnet and upstream the magnet. With two ridge detectors, we identify proton counts and pions. Then electromagnetic calorimeter helps to reconstruct electromagnetic particles. HCAL is a hadron calorimeter. And then the last part of the detector system is muon stations that identify muons. So having this precise vertex reconstruction and also powerful charge hadrons ID, we can do the analysis. Then LHCb covers a complementary range in PT and eta to central detectors, to ALICE, ATLAS, and CMS. This is well illustrated in this slide, that LHCb is complementing the coverage of CMS, for example. But for B quark production cross-section, it appears to be that the cross-section covered by LHCb is comparable to ATLAS and CMS, while LHCb covers much smaller solid angle. So we have a large trigger bandwidth for B physics and limited instantaneous luminosity. Then for the data analysis, the data sample that was used has an integrated luminosity of 2 inverse femtobarns collected at 8 TeV. So the signal channel is KC1 3872 decaying to J psi pi pi, predominantly through rho resonance. And then normalization is psi to S that also decays to J psi pi pi. For data selection, the first we have good J psi to mu candidates that are combined with 2 pions that are identified by rich detectors. So after all of that, the kinematic refit on data is performed, meaning that the dimuon mass is constrained to known PDG mass of J psi, and all 4 tracks, 2 muons and 2 pions, are required to have same origin vertex. Yes. So, and after that, the invariant mass spectrum looks like this. There is a huge peak from psi to S, and also very prominent peak from KC1 3872. You can see zoom here. Then another issue is that we need to distinguish prompt and BDK's components in the production. This is done using pseudo-proper lifetime defined by this formula. And then to have it, you need to know the Z position. Z means the beam axis position of primary vertex, also of decay vertex, and you need to know Z component of the candidate, Z component of the momentum for the candidate. To separate prompt and BDK's components, the simultaneous fit to invariant mass and TZ is performed. So this is well shown on this picture. So you can see here fit to invariant mass that separates signal from the background, and then here fit to TZ, where you separate prompt from BDKs. And you see here prompt component green and BDK's component. It's also green, but it is shaded. Ratio of yields of KC1 3872 and psi to S is extracted in bins of number of VELO tracks observed in VELO that I told is proxy to event multiplicity. So then the first quantity that was measured is the fraction of prompt, which is defined just as a ratio of prompt signal to total number of signal, prompt plus BDKs. It is also studied in bins of VELO tracks, so you can see a result on this plot as a function of VELO tracks. Black is psi to S, and blue is KC1 3872. So there is obvious decreasing trend for both of them, but normally the events with big quarks, they have naturally larger multiplicity than prompt events. On the other hand, the prompt production can be affected by in-medium effects, which is unlikely to happen to production in BD case. So after that, second and main thing that was measured is relative production cross-section defined here. So it is basically ratio of cross-sections of KC1 3872 over psi2s multiplied by corresponding branching fractions, and you need to know the prompt fraction for each of them. Yeah, thanks. And then the result is shown here. The red is prompt and the black is BD case. Let me start from prompt. This measurement in systematics dominated. Moreover, this systematics is correlated between the beams. And this measurement would benefit from having differential prompt production measurement, as we didn't have it yet in LHCb. So prompt clearly shows stronger suppression of KC1 3872 relative to psi2s at high multiplicity, which is expected if KC1 3872 is weakly bound state or has large radius. On the other hand, for BD case, there is no strong dependence. And the result is consistent with Atlas measurement. Then there is very new theory interpretation. I just briefly show it here. So you can see here comparison of the result to several models. Molecule is expected to have a sharp distribution, but compact tetraquark well fits into the data points. So the interpretation of the result is not so obvious, and also detector effects needs to be understood here. And then the next thing you would like to do is to measure production of KC1 3872 in heavy ion collisions. So we have this public figure already on that. So there is clear signal from KC1 3872 in P-lead. This significance is about 4 sigma. And smaller signal for lead-P. But this analysis is ongoing, and it will be complementary to other LHC measurements. You know, there is a recent result from CMS, for example. So this brings me to my summary. So the nature of KC1 3872 is important for understanding and testing QCD. LHCb devoted a rich program to study its spectroscopy, production, and decays. And the measurement of KC1 3872 production in proton-proton collisions with particle multiplicity was done. And the results show that prompt production of it is more suppressed than psi2s that at high multiplicities. That helps to understand the nature of KC1 3872 and suggests that KC1 3872 is more weakly bound than psi2s. However, you just saw the follow up from theory that shows that tetraquark fits into the picture. More production measurements are on the way. It is KC1 3872 production in P-lead, and also updated KC1 3872 production in proton-proton collisions with measuring differential production cross-section. So stay tuned, and thanks a lot.
Thanks a lot, Andrii. Indeed, you also saved some time, so there is more time for questions. So please raise your hand. So I have, well, first a comment and then a question. So the comment is about the plot in which you were showing the trend versus multiplicity for the prompt and non-prompt component. Yeah, you say that for the B, for the non-prompt one, you don't see any effect, but I don't know. I mean, well, maybe the uncertainties are large, but it seems that there is a sort of rising trend that indeed one may expect it because similar trend is observed also for beauty in general, right?
Yes. About these slopes, you can see that for prompt, what was measured is the significance of the slope, how much it is different from 0. For prompt case, it is 2.6 sigma. For BD case, it's slightly more than, it's like 1.5 sigma. But indeed, some trend is expected there, but much weaker than for prompt case.
Okay. And then in the next slide, if I remember well, yes, here. So can you tell us a bit more about what do you mean by detector effects to be understood here?
Here I mean that what we measure the production as function of number of velo tracks. Which is not the same as number of charged particles. So this detector effects that makes different these two quantities has to be understood if they play a role here or not.
Okay, so you need to translate from the reconstructed tracks to charged particles. Okay, I see.
Yes. But in principle, this paper shows that that this works very well for Upsilon production at CMS, and if it works for charmonium, then we can probably say that it's fair enough for this case as well. But yeah, it has to be understood.
Okay. So are there other questions? No? Okay, so thanks, Andrii, again. And
thank you.
We can move on. Next contribution is by Chiara Pinto.
Yes. Can you see the slides?
Yes, okay, so you can,
okay.
Yes, okay. So you can start.
Okay. Wait just a second. Okay. So good morning, everyone. I will present the latest results on light nuclei and anti-nuclear production in lead-lead collisions with ALICE, and I will present this contribution on behalf of the ALICE collaboration. In high-energy hadronic collisions, the LHC multivariant states are produced, and in this talk I will focus on the production of light nuclei and anti-nuclei. The production mechanisms are still under debate, they are not well understood, and they are typically described by two classes of phenomenological models, which are the statistical hadronization model and the coalescence one. In the first case, for statistical hadronization models, the hadrons are emitted from a system in statistical and chemical equilibrium. The yield is exponentially proportional to the ratio of mass and chemical temperature. And in the case of nuclei, which have a large M mass, they have a large sensitivity to the chemical temperature. In this plot, we can see that for lead-lead collisions at 276 TeV for the most central ones, the particle yields are of light-flavor hadrons are described over 9 orders of magnitude, going from pions to alpha nuclei, with a common chemical freeze-out temperature of about 156 MeV. In this model, the light nuclei are produced during the phase transition as the other hadrons, and the nuclei have a typical binding energy of few MeV. So an open question in this model is about how can such loosely bound states survive the hadronic phase environment, which, as I said, has a chemical temperature of 156 MeV. In the case of the coalescence model, the baryons which are close in the phase space and match the spin state can form a nucleus. In this sketch, for example, a proton and a neutron, which are close and match the spin, can form a deuteron, for example. In this model, the coalescence parameter BA is the key parameter, and it is tightly connected to the coalescence probability. In fact, to a larger BA corresponds a larger coalescence probability. This probability depends also on the system size, and for small distance in space, baryons are closer, therefore only the momentum correlations matter, and therefore we expect a large BA. In the case of larger distances in space between the baryons, for example, both the momentum and the space correlations matter, and therefore we expect a smaller BA. The ALICE detector is a general purpose experiment which has excellent tracking and particle identification capabilities over a very broad momentum range, and it also has a low material budget, which makes it the best suited detector at the LHC for the study of the light nuclei and anti-nuclei. In order to identify the light nuclei, we use the detectors in the central barrel, which are the inner tracking system, the time projection chamber, and the time of flight, and also the V0 detectors as multiplicity estimators. In the low momentum region, we perform the particle identification via the energy loss measurements in the TPC. As we can see in this performance plot, the helium-3 is very well separated from the other particle species over the full momentum range, and therefore it is identified using only the TPC information. And the other light nuclei are well separated from the other particle species, up to 1 or 1.5 GeV/c. For the extraction of the raw yield, we look at the N sigma distribution, which is the difference between the expected energy loss and the measured one, which is given by the beta block curve, which is the solid line in this plot. In this case, for the extraction, the signal extraction for helium-3, we also, which is represented here by the red Gaussian, we can also subtract the contamination from the other particle species, and in this case it is subtracted the contamination given by the triton, which is on the left of the helium-3. In the higher momentum region above 1 GeV/c, let's say, we perform the particle identification using the velocity measurements in the time of flight detector. And also in this case, I show here how we extract the signal. In this case, for the deuteron, we look at the mass squared difference between the expected mass and the measured one. Here I show some results of light nuclei and anti-nuclei transverse momentum spectra in lead-lead collisions at several energies. On the left, we show the results for deuterons in lead-lead collisions at 2 and 76 TeV. And on the right-hand plot, we show the analog results for lead-lead collisions at 5 TeV. Going from lower to higher energies, we increased a lot of the statistics, and therefore we could study several more multiplicity classes, which are represented in different colors. We fit the PT spectra with a blast wave function in order to extrapolate to the unmeasured regions in the low PT and the higher PT regions. As we can see here, from the ratio of anti-deuteron over deuteron, the yields are equal for the particle and antiparticles, so as expected, as it is expected at the LHC. We observe in this spectra, we observe an hardening with increasing centrality, which is also observed in other particle, light flavor particles. And in lead-lead collisions, it is related to collective motion. We also show here the results in different energies lead-lead collisions for helium-3 in several multiplicity classes, also in this case. We observe a similar behavior as that observed for deuterons, and we observe an hardening with increasing centrality also in this case. Finally, we also show the recent results for Triton on the left, and they are labeled with new, which from now on it is referred to for all the results released in summer 2020. And we have here the Triton in several multiplicity classes, and on the right, the first measurements of helium-4 that we measured in with Alice. Helium-4 and anti-helium-4. Here we have a summary of the blast wave fit of PT spectra going from pions to alpha nuclei. And as we can see here, we show in this dark green the helium-3 and in magenta the Triton, and these PT spectra are of the same order of magnitude, so they are considered comparable for the ratio to protons, as I will show in a moment. Here we show the deuteron to proton ratio as a function of multiplicity on the left, and the ratio to protons of helium-3 and Triton together as a function of multiplicity. We observe that, as we can see, there is a smooth transition across the different collision systems and energies, both for deuteron to protons and the helium-3 and Triton to protons ratio. So the light nuclei production depends only on multiplicity, and we compare these results with the expectations of the models. The coalescence models in magenta seems to describe very well this ratio for deuterons, and expectations for the thermal model, which only qualitatively describe the trend of data. In the case of mass number equal to 3, so in this plot, we observe in this plot, it shows the largest increase with multiplicity that can be found in light flavor data. And as we can see, the models do not describe very well the data points. So the results challenge the model in this case. We can also test the models looking at the coalescence parameter as a function of PT over A. And in this case, we show the B2 coalescence parameter for calculated for deuteron in several multiplicity classes and studied in lead-lead collisions at 5 TeV. We observe a rise with increasing PT over A, especially at higher multiplicities, so in these most central collisions. And this trend is described by the hydrodynamical calculations with the afterburner. Here in this slide number 14, we show the helium-3 and Triton B3 coalescence parameter as a function of PT over A in several multiplicity classes. And also in this case, we observe a rise with increasing PT over A and with increasing centrality. If we fix a slice of PT over A and look at the coalescence parameter as a function of the multiplicity, we can therefore test the coalescence model. And as we can see in this plot for deuterons for the B2, we observe a smooth transition from small to larger system size, and this trend is described by advanced coalescence, which takes also into account the size of the nucleus and the emitting source. Similarly, we also studied the B3 as a function of multiplicity for a fixed PT over A value, and also the B4. We have only 1 point for the B4, but for the B3 measured for Triton in lead-lead collisions at 5 TeV in red and in proton-lead collisions in green, we see that also in this case we observe a similar trend with multiplicity as for B2 and a continuous evolution with multiplicity, but the models seem to struggle to quantitatively describe the measured B3, and it seems so also the case for B4. We can also test the models studying the flow, the elliptic and triangular flow. The initial space anisotropy in non-central nucleus-nucleus collisions lead to an azimuthal anisotropy of the particle emission with respect to the symmetry plane. So this particle distribution can be expressed as a Fourier series where the Fourier coefficients are referred to as flow coefficients. The V2 is the elliptic flow and the V3 is the triangular flow. Here we show the recent results for the elliptic flow for deuterons on the left, for helium-3 in the central plot, and the first triangular flow measurements for nuclei on the right, which was measured for deuteron. We studied these elliptic and triangular flows in several multiplicity classes, and we observe an increasing trend with increasing PT and increasing multiplicity for both elliptic and triangular flows. We also compared the deuteron and helium-3 V2, the elliptic flow, with the other particle, lighter particle elliptic flow from pion to protons. And also for the light nuclei, we observe a mass ordering in the low PT region in all the centrality classes that we studied, up to 2 or 2.5 GB over C. We also observe an increasing trend with the PT, and especially for higher centrality classes. And this trend is expected from relativistic hydrodynamics model. So we compared the results for the coalescence and from the models for deuterons and helium-3 to the expectations of simplified coalescence and simplified hydrodynamics models. On the left, we compare the red points, which are deuterons, to the expectations of the simple coalescence, which is studied, which is calculated from the proton V2. The simple coalescence seems to overestimate the data in both centrality classes, and it seems to work better for more peripheral collisions than for more central ones. In the case of the simplified hydrodynamics, the expectations for the deuterons, which are the dotted red line, is calculated starting from a combined blast wave fit of pi, k, and p. And it seems to underestimate the data in this case, but it works better for more central collisions than for more central ones, for more peripheral ones, sorry. We also compared similarly to the same simplified models, the results of the elliptic flow for helium-3. And also in this case, we observe a similar behavior for this elliptic flow, and the V2 of helium-3 lies in between the expectations of the coalescence in red and the blast wave in blue expectations from these models. So the models partially describe the data, mostly depending on the centrality regions. Finally, we can compare the results to more sophisticated models and see how they are described. In this case, we compare the predictions, the data with the predictions of a hybrid model based on relativistic viscous hydrodynamics, which is the Jetscape 1.0, which does not foresee a coalescence in the final state. And as we can see from this plot for the V2 of deuterons, the data are very well described in the most peripheral, let's say the semi-peripheral collisions, from 20 to 40% of centrality, whereas the most central ones are not very well described. And if we add one more ingredient to the recipe, which is the coalescence in the final state, and we compare the results to the hydrodynamical simulation, EB Vishnu plus the coalescence in the final state, we see that the description seems to work better, and all the centrality classes are well described by the model's expectations, both for the V2 and V3 of deuterons and for the V2 of helium-3. But we do not have predictions available for more peripheral collisions. So we can study we can compare the results up to 40%. So this brings me to my conclusions. I show you that with Alice, we measured light nuclei and anti-nuclei up to helium-4, so up to the alpha. The production mechanisms evolves smoothly with multiplicity, and we compared all our results with the expectations of the statistical and the coalescence models, which describe different aspects of the light nuclei and anti-nuclei production. But we can say that the experimental results still challenge the models, and so stay tuned. And thanks for the attention.
Thank you, Chiara, for the very nice and complete talk. So it's time now for questions. I see a couple. So Yuri, please go ahead.
Yeah, thanks. So I actually have a question to your slide 19, I think, and 20. So that's a little bit confusing to me because you're discussing their coalescence and simplified hydrodynamics. So first of all, I'm not sure what you mean by simplified hydrodynamics. And second of all, the coalescence picture is put actually on top of blast wave or hydrodynamics. So what we call coalescence versus hydrodynamics on that slide, I kind of don't really understand. Could you please explain?
Okay, I'm not an expert of the models, but I can say that in this simple coalescence model, we start from the measurements of the V2 of protons, and we predict using coalescence, we predict the V2 of deuterons, and therefore we compare the results with these expectations. In this case, for the simplified hydro model, we start from the combined blast wave fit of the V2 of protons, kaons, and pions, and we predict the deuteron V2. And therefore, we compare the dotted line with the data points, the model with the data.
No, I meant that essentially, so what is coalescence? I mean, there is a certain evolution before coalescence happens on the left plot. So you don't produce hadrons right after the initial scatterings, right? There is a certain evolution before coalescence happens. So what kind of evolution is there? Is it blast wave? Is it hydrodynamics? Is it partonic cascade, hadronic cascade, or something else?
Actually, I'm not an expert. Maybe I can check with my colleagues and come back to you and tell you. I have to check.
You can continue the discussion on Mattermost. and we
Yes.
can take in the meanwhile other questions. So Boris Tomaszczyk, please.
Yes. Yeah, thank you. So maybe again, you might say you're not an expert, but I had exactly question to this plot, a combined blast wave fit. I mean, in blast wave there is no V2. You have to extend the blast wave somehow, and then there are a few ways how to extend the blast wave, and they work better or worse. So do you know how this blast wave model was extended here so the data are fitted?
I don't know if I can answer to your question correctly. So I would rather check before and then answer. Maybe it's better.
Okay, sure, I can read the paper probably. I thought that you might have a... Good, okay, fine, thanks.
Okay, so we have a question from Manuel Lawrence.
Yeah, also related, can you go to slide 16 where you show your beautiful new results?
Yes.
Now, of course, this blast wave has a dependence. This is, I guess, a blast wave fit with parameter T and beta. Do you know the dependence of the beta and T parameter for the blast wave going from central to peripheral or from large to small systems?
I think, sorry, I missed, can you repeat, please?
Yeah, so you have this blast wave plus this GSI Heidelberg model. And
yes.
The question is, do you have also a picture showing, yeah, right, showing the parameters of the blast wave fit as a function of the n, the eta?
Yes, it is an exponential slope trend.
Yeah, but is the beta and the temperature, are they going smooth or? So there's kind of hidden information. Yeah, maybe we can, I can also write this again to the MetaMost.
Yes, thanks.
Okay.
I have to check with my colleagues which worked on this. Yes.
There is a last question by Federico Antinori.
Yes, here I am. Sorry, I hadn't unmuted properly. I wanted to go back to the question from Boris. Chiara, if you can go back to the right. So what is done here, to my understanding, is very simple. You take on the left, you take the protons, and then you take the V2 of nucleons, and then you assume you just combine two nucleons, and that gives you a predictions for the V2 of the deuteron. On the right, you just take proton, kaons, and pions. You just fit the blast wave, and then you predict what you would get if your particle had the mass of a deuteron, and that is the red curve.
Okay, yeah, I think this was more an answer to a comment. So we can thank Chiara again, and now we can move on. So next speaker is Serguei Petrushanko from Moscow. You can start sharing your slide.
Okay.
Okay.
I'll try to go full screen.
Yes.
Okay. Can you hear me? Do you see me well?
Yes, you can start.
Okay, thank you very much. The title of my talk is Soft Probes in Heavy Ion Collisions with CMS, but this talk also includes our results on heavy flavors and Quarkonia. You know that CMS this is a nice heavy ion detector. We have a good tracker, wide colorimeter, and good muon station. All of this is in magnetic field near for Tesla, and using it we taking good data, heavy ion data. Heavy ion programs in CMS started almost 10 years ago. And till now, for this moment, we have exactly 100 published or submit heavy ion physics paper, which can be easily founded here on these links. But also we have a number of very interesting preliminary results, which hope later also to be in articles. And I would like to bring your attention to these links with these papers. We already have 2 talks about heavy ion physics at CMS. First was 2 days ago on hard probes. Yesterday we have diffraction, diffractive and inclusive processes in heavy ion collisions. And today, as I said, I will talk about soft probes, including heavy flavors and Quarkonia. Of course, during my talk, I can't talk about all of the results on this field in CMS, but I will try to concentrate on the newest result for latest 2 years, which became from the last ICHEP in Korea. First things I would like to start, charged particle multiplicity and transverse energy density. CMS put a point here on these histograms with these plots with versus colliding energy per nucleon pair. And CMS confirms that all of these dependencies, all of these 2 dependencies for all systems like proton-proton, proton-lead, lead-lead, they all follow power law. Flow, even at the very first days of the heavy ion collision in CMS control room, on CMS event monitor, we see an as it said, almond shape events when we see calorimeter response for non-central collision, which looks like an ellipse. You know, rich results, first results we get not in heavy ions, but in proton-proton at CNTTV. Then we get results in lead-lead collision and proton-lead also. We can extract elliptic flow from long-range to particle correlations and see one interesting thing that in proton-proton collision and proton-lead collision, I mean proton-proton collision with high multiplicity, the behavior of this V2 elliptic flow versus a number of tracks, registered tracks, this look very similar, especially if we compare with lead-leads, and we think that this is some kind of evidence of quality for origin of this in proton-proton. One of our new results dedicated to the mixed high-order anisotropic flow in lead-lead collisions. We prepare here some different high-order flow harmonics, and all have a qualitatively similar PT dependence. Interesting fact that this causes hydrodynamics with Glauber initial condition, and Sherry Losty doesn't provide simultaneous description of it, and we need to understand these things later. Xeon system, we also measured V2 in it, plot V2 versus for the different region of centrality versus PT. Interesting thing here is that for more central events, for the most central events, V2 in Xeon collision is slightly larger than those in which we found in lead-lead collisions. This can be attributed to the larger fluctuation component in these lighter colliding systems. We also measure V2 with 3 and V4. This is a comparison with lead-lead. And one thing that we do, we try to look difference approximation of it if we think that Xeon is a ideal sphere or have some nuclear deformation. And for most central collision for V2, we see that the hydrodynamical model with Xeon nuclear deformation is slightly better describe this ratio. I slightly go to the flavors. Here you see our 2 years ago results about V2 versus PT for heavy quark. We see significant positive V2 values which are observed for D0 mesons with PT greater than 2. The collective behavior of charm quarks in high multiplicity proton-lead collision is weaker than those for the light flavors. And the very new update we just shown at Hard Probe conference, we put also here our result for open beauty, and we see that no significant flow can be seen for this, at least in the systematic that we have. Another thing interesting here that we put some theory prediction for the open charm, hidden, and open beauty, and more or less okay. See more or less a key description of the theory with our data. Measurements, we do some measurement of V2, of Upsilon in lead-lead collision, and in contrast to gypsum mesons, which we have a good measurement by Alice, we see I talk about it today. And contrast to gypsum, as I said, no azimuthal anisotropy is observed with Upsilon mesons for our latest result, which was also shown at Hard Probes. Upsilon suppression. In lead collisions, we measured Upsilon and try to compare it with lead. In lead, we see all of the members of the family of Upsilon, but if you go to lead, and even in very high statistics CMS result, we don't see a third component of this family. And for the first and second, we see a very good suppression. Also new results, we do the same thing, but for proton lead. On the left slide, we see a proton. This on the right plot, this is proton lead. And here we see all of the members of the family, and also all Upsilon states we can find, and all of them are suppressed if compared with proton-proton collisions. On the next slide, we see how it's look if you plot a ratio for lead to proton and proton lead to proton. We see ordinal for both of these systems, ordinal of suppression, and of course larger suppression for lead collision. We have a talk today about this strange X particle 3872. CMS can find this interesting particle in lead collisions, and we have that our results, especially with comparison to another particle, help to understand the mechanism of production of such particle and the nature of it. Next slide. This is our first observation of the B0S mesons. With we get a statistical significant near 5 standard deviations. This is the first time in nuclear collisions, and the result here at that we see that there is don't see any significant PT dependencies of B0S B+ ratio. Model prediction, which we also plot on this plot, model prediction is reasonably well agreement with our data. On the right plots, you see yield ratio. This is number of particles, and B0S B plus ratio in PBS in lead-lead compatible with measurement in proton-proton. This is the first search for the top using lead-lead collision in CMS. This also new results. We using both charged leptons or charged leptons plus bit jets to see tops, and the measured cross sections are compatible with expectation from scaled proton-proton data and QCD prediction. Here you see boosted decision tree. As I said, we use both channels and two channels and hope that top quarks can probe both initial and final states, and later investigation give us some additional informations. I just need to add that background only that our significant close to the first standard deviation for both two methods. This is OC timeline and a few words about CMS upgrade. We hope very much to get new data, but of course with the current conditions, we hope that anyway in a year and a half we get some heavy ion events and collect more statistics with hope more with another systems. And after a long shutdown 3, we hope to get very much updated CMS detector with much more wider trackers, good MERN identifications, high granularity colorimeter and uncoupling region, and all other updates. And we hope using it to get new data. This is my summary. As I said, we get many interesting results and hope to have much more in round 3 and round 4. And in the very end of my talk, I just would like to put one slide from 2 years ago from ICHEP in Seoul. Of course, now we can't visit mass events like this. And it's a pity that I can't visit Prague and see the town and meet you face to face. But anyway, I would like to say to the organizer, Дякую многократно, and hope to see all of you again later. Thank you. That's all.
Thank you, Sergei, for this overview. I share your feelings. That's a pity not to be all together in Prague. Certainly, there will be other occasions, I hope. And yes. Okay, so it's time for questions now. Indeed, we have plenty of time for questions, so please. So I don't see hands raised. Let me check on the Matamos channel. No. So can you go to slide 15? Oh, yes, here. So yeah. So yeah, what is the PT interval of the last bin you measured? It's like 8 to 14.
I think it's something from 80 and more, as I understand.
Okay.
Then I don't see we collected too much statistic after 14 GeV.
Okay.
So I think 80 and more.
Okay, so you cannot go higher. Let's say you can more differential in PT at higher PT right now with the current data. You need.
Yes, this is the full range of our MERN colorimeters. 5 units of pseudo rapidity, and I don't think we have a big statistics for PT for big PT here to measure, and you know.
Okay.
I think yes, of course. Maybe later we will collect more data because who knows? Maybe at least we have to have a slight V2 for it, but on the current statistic, we can't measure it. We just say that in contrast, as I said, in contrast to GPSI mesons, for the moment we see no azimuthal anisotropy.
Yeah. Okay.
I think it's just for the moment.
Yeah. I have a similar question on the previous slide, indeed. So here, I mean, for open beauty, from this data, it's not clear whether there is or not flow. I mean, the uncertainties are still large. So, for instance, the last PT bin may even suggest that there is some non-zero V2.
Yes, and the model predicts something. I put here, not okay. CMS put here some prediction for D0 from these mesons, and in principle, they go close to it.
Okay.
You see the blue line here, a prediction from Jung et al.
Yeah. Okay, I don't know if there are other questions. Let me check. Seems not. So thanks again, Sergei. And we move to next talk, which is by Lukas Vermunt.
Yes.
From Utrecht. Okay, you can also turn on your camera if you. Okay, I see.
My camera is on, right? Okay.
Yes. Okay. So you can start.
Okay. Good morning, all from the Netherlands. I will discuss today on behalf of the Alice collaboration our recent measurements on open heavy-flavour production from small to large collision systems. Since it's recorded, I would like to start with a brief introduction. We also saw it earlier today already about the topic. So at heavy-flavours in Alice, we consider charm and beauty, which are produced in the hard scattering process of the collision. In PP, in small systems, you can describe them with perturbative QCD calculations that are based on the factorization theorem, which is shown here, and it's basically 3 ingredients. So we have the parton distribution functions that are non-perturbative. The partonic cross-section of the hard scattering, we can calculate the perturbative QCD, and then the third term is the fragmentation functions that are again non-perturbative and are usually taken from E plus E minus collision data. And recently it was found at LHC that this fragmentation part for charm quarks, especially for charm baryons, is not well understood. This was discussed yesterday in detail by John Wee. In physics, we are interested in the QGP, of course, this phase transition of nuclear matter to the deconfined medium, which we can recreate in ultra-relativistic heavy ion collisions. So we see the space-time diagram, the sketch of it here on the left. So when the nuclear collide after the pre-equilibrium phase, where we have strong electromagnetic fields, the QGP is formed, which expands hydrodynamically and freezes out into the hadrons we observe. And we are interested in this QGP phase, and for this heavy quarks actually an interesting probe. As you can see at the times depicted here on the slide, they are produced before the QGP and experience therefore and live a bit longer, so they experience the full evolution. In addition, they of course interact with the medium constituents, and they can even recombine with them. So this second hadronization mechanism we usually call recombination or coalescence. So like I said in the beginning, this is the latest result of Alice, a dedicated heavy ion experiment. We see here our detector, which is located at point 2. I will now flash the most important detectors for these heavy-flavour studies, starting with the most important one, the inner tracker system. So silicon detector closest to the interaction point, used for vertex tracking and PID. Then we have a main tracking device, the time projection chain, which is also very important for PID. We have a particle identification, the dedicated detector, the time of flight, and finally also the electromagnetic calorimeters are used for both triggering and particle identification. Then there are 2 more detectors for event properties, and mainly for the heavy ion collision. So we have the V0 detectors for triggering, centrality determination, and multiplicity determination, and the event plane estimation. And then along the beam pipe, we have the 0-degree calorimeters that are used in the directed flow measurements to estimate the spectator planes. In Alice, we measure open heavy-flavour in 2 ways. I will discuss now them both separately, starting with the fully reconstructed hadrons. Here in the top right, you see a list of the decay chains we study. So basically the D mesons, lambda C, and we have sigma C and the Xi C, where the latter 2 were discussed yesterday by John Wee in sessions, strong interactions and hetero, session 6. So these analyses are done on invariant mass based invariant mass analysis, exploiting the fact of the displaced decay topology of these particles. And also very important is the particle identification of the decay tracks. Secondly, we're looking at leptons and muons from heavy-flavour hadron decays, where the electrons are identified with PID using the relevant detectors. And muon tracks are measured at forward rapidity in the muon arm. The signal is then extracted after subtracting the hadron contamination and leptons and muons from non-heavy-flavour sources. And then we can make a difference between electrons from charm and electrons from beauty by making template fits of the impact parameter distribution, for which we can see an example here in the bottom right for semi-central lead collisions. Okay, so for the introduction, and next I will show our latest results, where I sometimes highlighted the new results, which means that they were released in the summer of 2020. I'd like to start with open heavy-flavour prediction in small systems in PP, and minimum bias 5 TeV collision data. What we see here on the left is the measurement of prompt D0s in red and non-prompt D0s in blue, where non-prompts are the decays of beauty hadron, D0s from beauty hadron decays. And then we have the similar plot for the D plus in the middle, and on the right we have heavy-flavour electrons, so coming from charm and beauty, where at low PT they're mainly from charm, and at high PT it's dominated by beauty. And they all compare to PQCD calculations, to photon to be precise, which are using this factorization theorem as showed before, with the fragmentation function based on E plus E minus collision data. And as you can see, it's actually doing quite a nice job in describing the data. So for charm, it's more on the upper edge of the uncertainty band. For the beauty part, it's close to the central value. And on this beauty, we'll have a dedicated talk in 2 talks from now by Xinye. We can go a bit more differential in PP, so by studying the open heavy-flavour prediction versus multiplicity. This is a recent study in PP 13 TeV, and which was motivated by 2 reasons mainly. First of all, if we can observe recombination of coalescence already in PP by looking at high multiplicity classes, and if this could explain the lambda C of a D0 puzzle, so the fact that the measurement of this ratio in E plus E minus collision data is significantly lower than the ones we see in PP. And this for this we would then look at low multiplicity data. The 2 main plots for this analysis we see on the slide. On the left, the lambda C of a D0, where the colors are the multiplicity classes, and we see that there's an increasing trend from low to high multiplicity in the intermediate PT range, but still the measurement is significantly higher than the E plus E minus measurement. On the right, we see the same measurement for D sub S over D0. Here, the picture is a bit different, as this ratio doesn't seem to depend on multiplicity, and it's actually also compatible with the E plus E minus value on within uncertainties. This again indicates that the fragmentation, the hadronization of charm baryons is not well understood, where the from mesons it's better. We can extend this to higher multiplicity by also adding the proton lead and lead data points, which we see here. Each subcanvas is here a different PT bin, where on the x-axis we now plot multiplicity, and on the y-axis the D sub S over D0 ratio. And the different markers are different collision systems. So if you look at the minimum bias proton lead points, open circular ones, together with the PP ones, the field cross markers, you see that the ratio is actually compatible between those 2. But then you go to lead, so the open the diamond markers, we see an increase, mainly at low PT, which is a combination of the strange enhancement we have in the QGP together with the charm recombination. Also, the ratio actually is compatible at low PT with the values predicted by the statistical randomization model. So that was the D sub S over D0. We can look at the same at the non-strange ones. It's shown now a bit differently. It's a double ratio of the D mass and abundances. So the D plus over D0 ratio in lead divided by the D plus over D0 ratio in PP on the left. And here we don't see a significant amount. It's compatible with 1, indicating that the D mass and abundance is not really changed from going from PP to lead. On the right, we see again the D sub S over D0. Now shown in the double ratio again. But now compared to where we see this sizable enhancement at intermediate PT, which is also predicted by models from transport models with Langevin equations that include both fragmentation and recombination. So we have the TAMU model here, the Quarkonia, and the PHSD. They predict different trends, but with the current uncertainties of our measurement, it's not yet possible to differentiate between them. So these results support the hypothesis that there's a relevant contribution of recombination in the charm hadronization in Ledlet. Then I would like to go to the nuclear modification factors at REA, which is the yield in AA collisions divided by the probability scaled ones at PP, and it's a probe of the medium energy loss, which can happen via elastic scatterings and gluon radiation. And it depends on the color charge, the quark mass, and the path length in the medium. So in this plot, we see the overview of the charmed hadron analysis of Alice in run 2. So with the lambda C in black, we have the non-strange d masses in green, where I want to point to the fact that the first bin is starting from 0 PT, which is important to extract the full yield in lead collisions also. Then we have the d sub s in orange compared to light flavored charged particles in light blue. First of all, we see in nuclear, we're seeing strong suppression for all of the studied particles here in central collisions. And we can make some conclusions about the different regions. So at low PT, we see that the REA of the d masses is quite a bit higher than the ones for charged particles, which is due to a combination of few effects. So we have the harder charm quark PT distribution and different fragmentation functions, but also different recombination and radial flow contribution. If you then look at the d sub s and the lambda c, we see that there's an indication of a less nuclear modification. So the REA is a bit higher, which is then which points to the fact that we have recombination again. So for the d sub s, it's related to the strange enhancement in the QGP, and also for baryons, we expect an enhancement when a recombination is there. At high PT, it's the REA values seem to converge for all the studied particles. So the measurement on its own is of course interesting, but we would like to compare two models also to extract more physics. This is done here. On the left, we see the prompt d mesons, we also saw on the previous slide. And on the right, we see heavy flavor electrons coming from charm and beauty, all compared to different transport models. So we have the list here. Some of them nicely describe the data, others are having more difficulty. But if you look at the models that do a good job, we see that there should be an interplay between hydrodynamic medium expansion. The charm quark loses its energy with collisional radiative energy loss mechanisms. And there should be hadronization via recombination for the charm. So then I want to go to the second observer we often study in heavy ion physics, the azimuthal anisotropies, which are coming from the fact that the interaction region when two nuclei collide as a geometric anisotropy, which is transformed by the pressure gradients of the QGP to an anisotropy in momentum. And this we study by looking at the Fourier transform of the momentum of the particles, and then we're interested in the harmonic coefficient. So for semi-peripheral peripheral collisions, as illustrated here, the second one is the most dominant one, the elliptic flow. It's actually the asymmetry between the in-plane and the out-of-plane directions. And at low PT, this is a probe of the participation of the charm quark in collective motion and also the thermalization of it. And at high PT, we can probe the path length dependence of the in-medium energy loss mechanisms. So on the bottom right, you see the V2 recent V2 measurement of Alice for the d mesons, for central collisions in red and for semi-central collisions in blue. As you can see, we've seen positive V2, indicating that the charm quark participates in the collective motion. Before going a bit deeper into the V2, I want to show the triangular flow, which was also recently measured, actually in the same paper by Alice. This is coming from event-by-event fluctuations in the initial distribution of participant nucleons in the overlap region. The sketch in the top right is now updated. And it's sensitive to the shear viscosity over entropy density ratio eta of S. So looking at the measurement in the bottom right, see again that we have a positive V3, a positive triangular flow for central and semi-central collisions for d mesons, indicating that the charm quark is sensitive to these event-by-event fluctuations. Going back to the elliptic flow, here we see the overview plot of recent measurements of Alice, of open heavy flavors with the prompt d mesons and electrons coming from beauty hadron decays, compared to hidden heavy flavors with the J psi and the Upsilon 1s, and to light flavor, the charged pions. And we observe positive V2 for all of them except for the Upsilon 1s, which is with our uncertainties compatible with 0. And we saw a similar conclusion in the previous talk by CMS. But yeah, our uncertainties are quite substantial here. In this plot, we can highlight three regions. The first one is P2 lower than 3 GeV, where we see a mass ordering in the V2 values, indicating that there's an aerodynamic expansion in the medium. Then when we go to 3 to 60, we see that the V2 of the d-mesons actually get to the same level as the one of light quarks, indicating that we have heavy quark hadronization via recombination with floating light quarks. And then at high PT, the V2 values seem to converge, indicating that there's a similar path length dependence in the energy loss mechanisms for heavy and light particles. Again, here the measurement itself is interesting, but we want to compare two models, which you see here. So we have the V2 in the top row, the V3 in the bottom one. On the left, we have the central collisions, and on the right, we have semi-central collisions. And we compare them now again to the transport models of charm quarks in an hydrodynamically expanding medium implemented via the Boltzmann-Langevin equations. And yeah, if you see that the models that have fragmentation and recombination in them fairly describe the VN harmonics, some of them do better, some of them less. And from this, we can go extract a bit more physics by looking at the diffusion coefficient ds, which is related to the terminalization time of the charm quark following this equation. So if you look at models that describe the VN harmonics with the reduced chi-squared of lower than 2, we can put an upper and lower and upper limit here on this d sub s, which leads to a charm terminalization time between 3 and 14 Fermi over C, compatible with the lifetime of the PGP. Finally, I also want to show the first harmonic coefficient, the directed flow, actually the charge-dependent directed flow, which is an asymmetry between the forward and backward emission, and can be used to study the pre-equilibrium time dynamics of the collision, where we expect strong electromagnetic fields, and we can use this charge-dependent V1 to study the time dependence of it. Also, the initial tilt of the matter and actually the electric conductivity of the PGP can be are sensitive to these to this V1 measurement. Charge currents are due to a combination of two effects, actually competing ones. So we have the Faraday effect on one edge, which is the electric field induced by the decreasing B field during the collision. And we have the Hall effect, which is the Lorentz force induced by the moving charges, where the moving charges are here the spectators. So the charm quark is actually an ideal probe for this for two reasons. Because the formation time, as we saw in the introduction, is comparable when the B field reaches its maximum. And also the relaxation time is similar to the QGP lifetime. Therefore, expect a larger effect compared to light hadrons. So yeah, on the right we see the actual measurement of the delta V1. So the V1 of the D0 minus the V1 of the D0 bar. And there's a hint of a positive slope, which we try to quantify by fitting a linear function. And actually, we found this value with a significance of 2.7 sigma. Comparing them in the same paper, we also show the light flavor. So we have the charged hadrons, where there's a similar trend observed with a different magnitude. So note 10 to the minus 3 in the top left. And both these measurements challenge some recent theoretical calculations where that actually predicted a negative slope and an order of magnitude smaller than both the charged hadrons and the D0s. This brings me already to the conclusion. So yeah, with Alice's unique vertex and PhD capabilities, we had some crucial heavy-flavour measurements in run 2. And what we learned so far, I've listed here a few points. So the heavy-flavour production cross-section and PP collisions are compatible with PQCD calculations. You also see that the hadronization of charm quarks is already modified in PP collisions, mainly for charm baryons. If we go to lead, we see a strong nuclear modification of the charmed hadrons, both mesons and baryons. You see that the mesons also participate in the collective motion of the system. And finally, we see multiple occasions that the recombination is needed to describe charm hadron collection in that lead. That is all I had. Thanks for your attention.
Thank you, Luke. You also saved some minutes, so we also have more time for questions. So let me see whether someone has a question. So the talk was indeed very clear and very complete. Let me check the Mattermost channel. So I have a question here. Well, you saw it also from this slide. From the conclusion, you have the bottom left plot. Yeah. So, what are the chances to go to lower PT for lambda c? I mean, now and in the future.
I think already now we can go a bit lower for lambda c. So the lambda c in there's a preliminary measurement. We're working on this. It's a LED 2018 set, so we don't have more data, but we're working on it to extend to lower PT. I think maybe one extra bin is possible.
Okay. Let me see. No question. Okay, so we thank you again, and we can go to next speaker.
Yes, hello.
Yeah, it's Lukas Kramarik from Prague. So you can share your slides.
Okay, and I will share my video.
Okay.
So is everything working fine?
Yes, you can start.
Great. Okay, hello. Thank you to organizers for giving me the opportunity to present here. I would like to present the review of the star measurements of open heavy hadrons in gold-gold collisions at 200 GeV. Firstly, I would like to show you why we want to measure QGP with the heavy-flavour hadrons. Then I will briefly introduce STAR, so solenoidal tetrahedric, and I will show you finally I will show you results on heavy-flavour energy loss, directed and elliptic flow of charm, and hadronization of charm quarks in gold-gold collisions. As we probably know, so QGP is a hot medium that is created mainly in the central heavy ion collisions. And heavy-flavour quarks are expected to be created at the initial stages of these collisions, so mainly in the hard scatterings. So they are expected to experience the whole evolution of the system, including this QGP phase. And by measuring these heavy-flavour hadrons, we can probe the predictions of the quark mass dependency of energy loss. Also, by measuring their collective behavior, we can measure the degree of thermalization in the QGP or constrain the quark diffusion coefficient. So this presentation is focused mainly on open charm hadrons. At STAR, we are able to reconstruct them using their topological hadronic decays that are listed here. So STAR, so it's an experiment that is situated at the Relativistic Heavy Ion Collider at Brookhaven National Laboratory here in the USA. It was designed to study this QGP. Most of the tracking and PID detectors are immersed in the magnetic field, and they have the full azimuthal coverage and excellent tracking and PID in the mid-rapidity. So one of the most important detectors for the analysis that I will present is time projection chamber. There is a gases detector that track and identify particles in it using the energy loss. In this detector here we can see the nice plot of energy loss versus the momentum of tracks, and we can see nicely separated protons, counts, and pions. Another detector that even more help us to identify particles time of flight, and this one measures the velocity of the particles. And on this plot we can see 1/, velocity versus momentum, and here we can see even clearer separation of charged hadrons. Forward meson spectrometer is the detector that in this presentation will help to measure the event plane of the collisions. So it's a very forward detector. And we have barrel electromagnetic calorimeter that help us to trigger and identify mainly high PT electrons or leptons. And the most important detector for the presented analysis is the HFT. It was used in all of the analysis that I will present. So it's a silicon detector that was at star from 2014 to 2016. At the right upper plot, we can see how it greatly improves the resolution of tracks in XY plane and in the Z direction. Thanks to this, we have significantly improved our signal to background in reconstruction of open heavy flavor. So firstly, I would like to show you results on the energy loss in gold-gold collisions. So as I think most of you know, so we evaluated using the RAA, that is the ratio of particle production in gold-gold divided by the particle production in PP and scaled by the nuclear overlap function or number of binary collisions. So here we can see the results that we published some time ago. So this is for D0. The blue ones are with the HFT, so we can see that it nicely improves the uncertainty compared to the previously published results without HFT. We can see it for 3 different centralities. So upper one are the central collisions, the middle one is semi-peripheral, and the lower one are peripheral collisions. We can see that for PT higher than 3 GeV, the suppression is clear in central collisions. However, it disappears toward more peripheral collisions. For a lower PT, it seems that the suppression is same across all centrality intervals. We have also compared our measurements to the results from ELISE that measure it in lead at higher energies. We can see that it's nicely consistent. And the lower plot shows us the comparison to the charged pions, so the pions, sorry, and charged hadrons at star, and we can see that these are also nicely consistent. So these results hint us that charm quarks lost significant energy in the formed QGP. In addition, we calculated the nuclear total production cross section of D0 per binary collision. So in case of gold-gold collisions, the upper plot shows us its dependency versus centrality. And we can see there is no clear dependence, so it doesn't depend on the centrality. And we see that it's systematically lower than the production in proton-proton collisions. We did the same measurements with the D+, D- mesons. So these are presented in more details in a poster by Jan Vaněk. Here we see the same centrality classes. The upper plot shows us the nuclear modification factor. The red points are D+-, and we can see that these are clearly and nicely consistent with the D0s from the previous slide. The lower plots show us the ratio of D+ to D0, and this one is consistent with the PDA calculation. So we have also measured the energy loss of heavy flavor decayed electrons. Here we also use the HFT that enables us to measure the DCA of these electrons that is shown in the left upper plot. Thanks to this, we can extract charm and beauty electron fractions using the template fits. And using them the template fits and extract them from the background photonic electrons and hadrons. The right plot shows us the result of these measurements. That is the RAA for charm decay, that is the red one, and it's for higher PT, it's consistently at the level of 0.4. And we have also measured the beauty decayed electrons RAA that is higher than charm decayed. And if we make the ratio of them, we can see that if we have measured less suppression of beauty decayed electrons with significance higher than 3 sigma. So on this plot, on this slide, there's another measurement that helps us also to understand the hadronization of charm. So this is a measurement of lambda C to D0 yield ratio. So it's a baryon to meson ratio for charm hadrons. Left upper plot compares it to previously measured strange baryon to meson ratio and the light baryon to meson ratio. We can see that in the measured PT interval, these are nicely consistent in gold-gold collisions. The lower plot shows us multiple models and how they compare to our measurements. So we can see that also in the measure, even in our measured PT interval, we can constrain some of the models. Here we can see that, for example, Quarkonia model that have both coalescence and fragmentation hadronization of charm is nicely consistent with data, and also the Xinye model that has this sequential coalescence hadronization of charm. On the right plot, we can see dependence of diverse ratio on the centrality of collisions. So towards the right is higher number of participants, so more central collisions, and we can see some slow rise. That is, but this one is consistent with the lighter baryon to meson ratios. Another ratio that we measure is ds to d0. So this one probes, in addition to coalescence, it probes the strangeness enhancement. In this right plot, upper plot, we can see this ratio versus PT and how it compares for 3 different centralities. We can see that this centrality seems to be consistent, and the ratio is higher than in the PT simulation. A lower plot shows the comparison with ELIS measurements in LED at 5 TeV. We can see that in the measured or in the PT interval where these experiments are measuring, it's the ratio is same, and we can see that ELIS results from PP are nicely consistent with PTA. Here we compare this ratio to different models. So you could see the models from the lambda c to d 0 ratio. So the upper plot, you can see the Quarkonia coalescence and fragmentation model, coalescence plus fragmentation hadronization model. And this one is consistent with data mainly for lower PT beams. And on the lower plot, you can see the Xinye model that has sequential coalescence hadronization, and this one is nicely consistent with the measured ratio. So from this, we can conclude that charm quarks participate in the coalescence hadronization in the QGP. So using all of the presented measurements, we can calculate the total charm cross-section in gold-gold collisions. So we calculate it as a total charm cross-section divided per binary collision. So for D0, the measurements goes down to the 0 PT. For D plus and DS, we fit the measurement and extrapolate it down to 0 PT. For lambda C, we use the presented lambda C to D0 ratio that is fitted by models and then extrapolated. So if we sum it up, we see that in gold we have 152 microbars cross-section per binary collision. That is nicely consistent within uncertainties. That is within uncertainties consistent with the proton-proton charm cross-section. So this measurement and this calculation suggests that charm quarks are formed the same way in the gold-gold and proton-proton. However, they are differently distributed among the different hadrons. So another variable that we measure is V2. So here we can see the Fourier expansion of the particle yield that was already presented today. And these V coefficients are the so-called flow coefficients. If we take the coefficients V2, so it's elliptic flow that describes how the medium created in the overlap region of the collision is expanding. From light flavor measurements, we see that there's some hydrodynamic behavior of the created matter. On the left plot, we can see how this V2 looks like versus PT for D0 and for lighter hadrons. These measurements has a better statistic uncertainties. These are combined 2014 and 2016 runs. And we still see the same trend. So for PT higher than 2, there is no difference between light and charm meson. And for lower PT, there is a clear mass dependence. On the right plot, we can see what happens if we divide the V2 by number of constituent quarks. And we see that results are consistent for light and charm, and this also suggests that the charm quarks flow with the QGP. So we did the same measurements again with heavy-flavour decayed electrons. So upper plot shows us the result of charm decayed electrons, the black points, and we compare it here to the D0 V2 from the previous slide. This one was folded to decayed electrons with semi-electronic decays from the simulation. We see that these two measurements are nicely consistent. Additionally, we measured the beauty decayed electrons V2. That is a lower plot. Here we can see two different methods of extracting the event plane. So the already introduced FMS detector. So here the very important part is the gray box, that is the systematic uncertainty coming from non-flow. And we can see that this FMS detector nicely limits this uncertainty. Also, if we calculate the hypothesis of the zero flow, we see that beauty decayed electrons have a non-zero flow with significance at 3.4 sigma. Here I just briefly want to show you how the V2 of heavy-flavour decayed electrons looks like in other collisional energies. So we have measured it in gold-gold collisions in 27 and 54.4 GeV. So left plot shows us the comparison of this V2 for these three collisional energies. And what we can see is that for 200 and for 54.4, the V2 is same. And there is some hint that it might be lower in 27 GeV gold-gold collisions. And the right plot shows us the comparison of these two light flavor, and we again see that for 54.4 GeV collisions, the heavy flavor decayed electron is V2 is consistent with light. However, for 27 GeV, it again seems to be slightly lower, and this brings us to the conclusion that heavy quarks interacts strongly with the medium, also even with the medium even in 54.4 GeV. And another coefficient that we measure is the directed flow, or V1. This one is important to study the initial conditions of collisions. So from hydro, we can learn how the bulk created in the collision is tilted. In addition, we can probe the initial electromagnetic field that is predicted to have opposite effect for charm and anti-charm. And it since charm is created much sooner or earlier than light flavor, so it should induce larger V1 for charm quarks. So here is the result of our measurement. So we can see the red points that are the D0 V1 compared to the empty squares that are the K-counts. We can see that the V1 of D0 is much larger than for counts. We see also comparison with the models. Here the slope of the predictions are same as in the data. However, their magnitude is much lower. Thanks to comparing models and this data, we can nicely constrain initial conditions. And here again is to compare is the measurements of charm decayed electrons V1 that are these. That is compared to this D0 V1 from the previous slide. And we can see that these two measurements are again nicely consistent. And this slide, we see the probe of the electromagnetic field effect. So on the left side, we can see the V1 versus rapidity for D zeros and anti-D zeros. And on the right side, we can see it for positrons coming from charm decays and electrons coming from anti-charm decays. And for both cases, within an uncertainties, we don't see any splitting due to the electromagnetic field. And this brings me to my conclusions. So we have measured that, clearly measured that the meson production is strongly suppressed in gold-gold collisions. We also saw a suggestion that there is less suppression of beauty decayed electrons compared to charm ones. We have measured elliptic flow, and we see that the charm quarks gain significant elliptic flow and they achieve local thermal equilibrium in the QGP. And from measurements of the directed flow, we can learn about the initial conditions, and we have no observed charm and anti-charm splitting due to electromagnetic field. And finally, what is important is that the charm quark cross-sectioning per binary collision in gold-gold collisions is same as in PP. However, the hadronization androchemistry is significantly modified. So thank you for your attention, and here is the list of star presentations and posters at this conference.
Thanks, Lukas, also for the perfect timing.
Thanks.
So it's time for question now. Jeremy, go ahead.
So I have a question to slide 17, where you present the total charm cross-section. I'm just wondering if you have any, if you make any assumptions here on the contributions from the heavier charm baryon states, such as the Xi, because in principle, these should also contribute to the total d sigma dy.
Yeah. So it's not here in this table clearly. However, yeah, it's not here. But the question is how much of them is produced at star energies.
Yeah, I was wondering if there was any assumption made when calculating the total.
No.
Other question? In the meantime, related to this, can you say a few words more on how you extrapolated the lambda C spectrum down to 0 PT? Do you, if you know?
Yeah, I'm not the analyzer, so I don't know much details, but I know that they use these model calculations as it's shown in this slide. So that they use the model calculations, feed the data.
With the level fit.
Yeah, yeah, but I'm not sure.
Okay.
More details.
Yeah, and
yeah, but yeah. Okay, sorry.
No, please go ahead.
Yeah, I think that they are fitting the lambda C to D0 ratio in this case. So.
Okay, I see. Always, if you know, in PP you don't have a measurement of lambda C, right?
No.
So my question is actually I have two questions. First is whether there are plans for measuring it. And second is, what did you assume in the proton-proton cross-section that you report in the table here to come from lambda C?
Yeah. So here's the reference for this number. So there is more details, and this is mainly from the mesons, D star and D0, and according to plans, so. Currently, this PP reference has a low statistic at star, and it also limits the RAA and gives the main part of the uncertainty in RAAs. But in the future, there is a planned some PP 200 GeV run at RIC, so it might get better. But it's in 2023, so we'll see.
Okay. I have also, let me see first if there are other questions. Seems not. Let me check the Mattermost channel. Okay, no, there is another thread ongoing there. So if you can go to slide 13. Yeah, yes. So here, here is minimum bias basically, but your uncertainty are not that large. Can you do a centrality differential measurement? If you know.
Yeah, I'm not sure if they are planning to do so for now, but I can ask and let you know.
Okay, I have a last curiosity about slide 20.
20, okay.
Yes. So here, when you go to low energy, I assume that you might become more sensitive to non-flow contribution. Indeed, you also show a band showing, yeah. So indeed, I was wondering, can you say a few words on which method you use for measuring V2 here, also at the lower energies?
Yes, sorry, I'm not an analyzer here, so I don't know much details how to extract the V2.
No, okay, no,
Sorry
don't
for that.
worry. No, but you presented many results, so don't be concerned about this. No worry. Okay, so let me check whether there are other questions. Seems not.
No,
so
I can just quickly answer your question, Andrea. It's event plane method here.
Okay. And the event plane you estimate in the same region of the electrons?
No, I think event plane is what Lukas showed at one of the first slides for the forward.
Okay, yes, okay.
Detector.
Yeah, fine. Okay, thank you, Barbara.
Yeah, thank you.
Okay, so we can here we can thank Lukas again, and we can move to the last talk of this session by Xinye Peng from Wuhan.
So can you see the slide?
Yes. So okay. you can start.
Okay. Let me full screen. Wait a moment. Okay. So first, I'd like to thank the organizers and the Alice collaboration to provide this opportunity to give a talk here. So today I will discuss about beauty production and anisotropy with Alice at ICHEP Energy. So beauty quark. So as we know, in heavy-ion collisions, beauty quark are produced in the early stage of the hard scattering processes. So due to its large mass, they are produced earlier than the QGP formation time at ICHEP Energy. So they will experience the whole system evaluation and the interaction with the medium in lead-lead collision. So they are very effective probes for the properties of the QGP. In particular, as we know, beauty quark will lose their energy by the collisional and radiative processes in heavy-ion collision, and compare the result with lead-flavour and charm quark result. It can help to understand the color charge and the mass dependent of the energy loss. Besides, we can also test whether beauty quark participate in the collective motion of, and symbolized in the medium via the flow measurement. What's more, in PP collision, it can provide the baseline for P-lead and lead-lead collision and test the perturbative QCD calculations at ICHEP Energy. In P-lead collision, it can help isolate the initial state and cold nuclear matter effect. So ALICE is dedicated to study the properties of QGP. In the central barrel, we have the inter-tracking system, ITS, time projection chamber, TPC, time of flight detector, TOF, used for vortexing, tracking, and charge particle identification. We also have the electromagnetic calorimeter and can provide information of the trigger and the electron or neutron pion photon identifications. At the forward rapidity, we have some small systems such as the V0 and the ZDCs provide the event trigger and the characteristics. So, in this case, Alice can perform a lot of different beauty measurement. So this talk will cover the hadronic decay, no prompt, D meson, B decay to D0, D plus, D sub s, and the semileptic decay, beauty decay electrons, and the beta jet measurement, and also the no prompt gypsy ones. And here is the data sample used for this analysis and covering different systems from PP to PLAD and LAD collisions. So before I go to the result part, I will have a brief introduction of the analysis technique. First, start from the beauty decay electrons. As we know that we are the semileptic decay, we have very large branch ratios, around 10% for beauty decay electron. So we can have more precision of the measurement. And we also know that beauty hadrons have a longer lifetime than the charm and other electron sources. So according to this property, we can first calculate the impact parameter with respect to the primary vortex. And according to these distributions of different sources, we can use the template fate of the impact parameter to obtain the beauty decay electron fractions. Similarly, for the no prompt gypsy, we can use unbiased ambient 2D likelihood method fate on the invariant mass and pseudo proper decay length distributions. So then when I go to the no prompt D mesons, no prompt D0, D plus, D sub s. First, according to, we first build the secondary vortexes, and according to this the property of the secondary vortex, we can build different decay topologics, such as the impact parameter, the normalized decay length, so the pointing angles, and so on. With this as the input, we can use a new machine learning method to simultaneously increase the beauty decay D meson fraction and separate the combinatory background. And then the signal can be extracted via invariant mass analysis. You can see here, I take the D sub s as an example. With this new method, we can obtain the D sub s signal with the no prompt fraction around 60%, but also with a good quality of the fit. Then also thanks to the new machine learning method, it can help us to obtain the different raw yield with the raw yield cut with different no prompt fractions. Then we can use the efficiency of the charm and beauty to do the simultaneously fit and obtain the no prompt fraction. For the bit target jet, first jet was reconstructed via the anti-KT algorithm with the R equal to 0.4. Then we can apply different topological cuts to increase the B-jet fractions, either on the significance of the secondary vortex displacement or the minimum number of tracks in a jet with a large impact parameter. So then the B-jet fraction and can be obtained either on the model-based method or the data-driven method. And for the model-based method, also thanks to our data, and it can help to constrain, especially at low PT, and reduce the systematic of the method. Okay, then I go to the result part. Start from the result in PP. First, Alice has measured the no prompt D0, D plus, D sub s cross-section in PP at 5.02 TV. You can see from the left-hand plot. Then takes the no prompt D0 as an example. In the middle rapidity, we compared the prompt D meson from the red point and the no prompt d meson from the blue point with the band range from the follow calculations. And you can see within uncertainty, the data lays on the upper edge of the phono for both charm and beauty, the prompt and the no prompt D0. And with these two cross sections, we can also calculate the ratio of no prompt cross section over the prompt one. And for both D0, D plus, D sub S, you can see here. So this ratio for these three different D mesons, the ratio is compatible with each other within uncertainty. And the shape of the ratio can be explained by the different PT shapes of beauty and charm. As we know, the beauty spectrum, initial spectrum is harder. And also this ratio can help to constrain the beauty decay, D meson decay branch ratios. And similarly, Alice also measured the beauty decay electron cross section at 5 point in pp at 5.02 TeV, and also the no prompt Jep psi cross section in pp at 13 TeV down to low PT. And both these two measurements can be also described by the phono calculations within uncertainty. The Alice also have the B target jet measurement. You can see from the left-hand plot is the first Alice measurement of the B target jet cross-section in PP at 5.02 TeV down to low PT equal to 5 GeV over C. And you can see the measurement can be described by different POHAG plus PCR simulations within uncertainty. And with the ratio of the B target jet in P-lead collision and over the nucleus in lead nuclear times the cross-section in PP, we can have the RP-lead measurement. So you can see from the right-hand plot, Alice measured the B target jet RP-lead at 5.02 TeV. You can see our result is the red point. It's extend the existing CMS measurement down to low PT. And you can see the RP-lead result is consistent with the unity within uncertainty, which indicates that the cold nuclear matter effect is not significant. And then we can shift to the result in lead-lead collision. First, Alice measured the beauty decay electron RA in 0 to 10 and 30 to 50% in lead-lead collision at 5.02 TeV. Here I only takes the 0 to 10% result as an example. You can see the beauty decay electron result from the red point and the blue point with different eta on the rapidity coverage. And we can observe that the separation of the beauty decay electrons. If we look together with the inclusive beauty and charm decay to electron, the open black point, we can find that although with a very large uncertainty, we can notice that at low PT, it gives a hint of the RA of beauty decay electron is systematically higher than the inclusive ones. While at high PT, these two results are compatible with each other. As we know, beauty decay electrons are the dominant sources in this PT range. So although we need more accuracy to understand this measurement, but it gives a hint of the mass ordering of consistent with the mass ordering of the quark mass dependent on energy loss. And also this measurement can be described by the model calculations include the collisional and radiative energy loss, which is important in lead-lead collision. We also have more precious measurement of no prompt D0 RA in lead-lead collision at 5.02 TeV. You can see from the left-hand plot, the blue point is no prompt D0 measurement in 0 to 10%. And we can also observe the separation of the beauty decay D0 in the intermediate PT. If we look together with the red point of the prompt D0, the charm decay D0, once it gives a hint of the ordering of RA of beauty decay D0 is larger than the charm decay D0s as in the intermediate PT. And if we look at the middle and the right plot for the RA of no prompt D0 in the 0 to 10% and 30 to 50%, we can find that the RA of at 0 to 10% is lower than the ones in the 30 to 50%, and this can also be being described by the model calculations, including the collisional and the radiative energy loss with uncertainties. So with the RA of charm and the beauty, we can calculate the ratio of no prompt D0 over prompt D0. You can see this very nice plot at 0 to 10 and 30 to 50% from left and the right-hand plot. And for this, we can observe that at a low PT, for PT less than 5 GeV, we can observe some pattern which hint of the different shadowing of flow or decay kinetics for the charm and the beauty from the model calculations. Well, for the high PT part of PT larger than 5 GeV, we can find that the result is systematically higher than unity for both these two centrality classes, which indicates that beauty quark undergo less separation than the charm, which is also consistent with the mass ordering of the energy loss. So finally, I will show the result of the beauty decay electron V2. You can see from the left-hand plot, it's the beauty decay electron V2 at 30 to 50%. And thanks to the 2018 large data sample, we have the significance of 3.75 sigma for the no-zero elliptic flow of the beauty decay electrons for 1.3 to 6 GeV. So the data can be described by the model calculation, different model calculations with uncertainty, except the elliptic blast wave models. While in these models, it have very extreme assumptions with the beauty is fully thermalized in the medium. Of course, we know it's not this case. Well, also shows the V2 families of different kind of hadron spaces measured by Alice for the charged pions, prompt D0, inclusive gypsy, and the beauty decay electron, the optional V2s. Here, it's already been discussed by other speakers, so I will not go to details of that. But here, I want to mention that we can find that the open beauty V2 is systematically higher than 0, while for the Bottomonium optional V2 it's consistent with the unity although with the large uncertainty. Okay, it brings me to the summary. First, beauty production has been measured in PP, PLED, and lead collision with Alice. So in PP collision, the production of the cross sections of both beauty decay, d mesons, electrons, jet size, and the b target jet can be described by the perturbative QCD calculations. In the p-led collision, the R-p-led of b target jet result is consistent with unity, and in lead-lead collision, our beauty measurement of beauty decay electron, the no prompt d meson result are important constraint of the mass dependent of the energy loss. Finally, Alice also measured no zero beauty decay electron weights. That's all from my side. Thank you.
Thank you, Xinye. So we have time for questions. I don't see hands raised. Let me check the Mattermost channel. So concerning the comparison of the non-prompt, of the ratio of the non-prompt RAA to prompt RAA, there is these structures that one sees in the theoretical predictions, I mean, the ratio of theoretical predictions. Do you know, I mean, a bit more about the details that behind in the models that lead to such trend? Can you say a few words more?
Thanks for this very good question. And of course, I know a part of the reasons, but of course, it's not fully covered. So from some of the theoretical authors, they told us that firstly, the magnitude of this ratio can be related to the coalescence. So whether include the coalescence or not can have different magnitude of this ratio. Of course, for this model list here include the coalescence, and also for the patterns here. For the PT from 2 to 5G, or say it can deal to the radial flow push or the different decay kinetics. Well, for the low PT, for PT less than 2G, we will say you can see it gives the hint of the increase of the measurement. The magnitude of the increase also can be affected by the difference of the shadowing of beauty and charm. Yes.
Okay. Thank you. So let me see whether there are other questions. Seems not. So concerning the beauty electron V2, so yeah, at low PT, the uncertainty is still large. The statistical precision is still rather poor, and but it seems that the data are above the model expectations, though I think one cannot conclude right now. Yeah. So what are your plans for improving this measurement or accessing beauty, maybe in other ways like non-prompt V2? So do you know what is the plan? Is this the last word on the beauty electron V2 from run 2?
Yes, I think it's already used 2018 large statistic sample. So I think it's for the beauty decay electron V2. It's the final version, I think. So if we want to the more precious measurement, we need to go to wait for the run 3. And of course, for other no prompt D meson, such as you mentioned, for the no prompt D0, we already, as you already say, the RA measurement with the same technique, we are trying to have the V2 measurement. Of course, we know from the technique side, we have no problem, but the problem is the current statistic, whether enough for us to analyze the V2. But of course, we are not trying to do that. Yeah.
Okay, so thank you. I don't see other questions coming. Let me check again the Mattermost channel. So there are no other questions. So Okay, so let's thank Xinye again, and this session has finished. So thanks a lot to everybody for connecting, and the next heavy-ion session will be tomorrow morning, starting at 8. Yeah, so have a nice day or evening, depending on from the place where you are connected from. And bye-bye to everybody.
Thank you, Andrea. Goodbye.
Bye.
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 Bye.